Ora si registrerà la conferenza.
So, please, Christian, the floor is yours.
Okay, yeah, thank you very much, Valerio, and all the organizers of this workshop for giving me the opportunity to present some of my work related to heat waves. So that's in collaboration with all those people down here. The first part I'm going to talk about was mainly done by Jion Ma, a former PhD student. And the second part is then a collaboration we did here at the ICCP Center in Busan. So if I might not have to introduce the topic of heat waves and why they're important for this workshop very much. Just a few slides here, just some example slide for European heat waves, example here from July 2019, where we also experienced, say, in France and the Benelux countries, temperatures above 40 degrees. And heat waves, that's actually one of the major sources of fatalities due to natural or climate-related hazards in Europe. So here you can see here the mean and median of the number of people who might die per year due to heat wave events in Europe. If we would go back to the 2003 heat wave in Europe, then almost 70,000 people died. So that's kind of illustrates the importance of this topic and that we might be able to understand the dynamics behind heat waves better, and which then might lead us to potentially predict them more. So besides Europe, we also have heat waves in Asia. So this year, but also last year, especially India and Pakistan, they experienced extremely hot temperatures, also above 40, 45 degrees. Here you can see some list of cities with population of more than 1 million people, and they experienced maxima of up to 45 degrees, which is, of course, relatively extreme. So typically, if we talk about heat waves, we kind of mainly think about temperature, but actually also the relative humidity is very important, especially for the health impacts. So here I show on this graph here basically the relationship between temperature, x-axis, and the heat index. That's the different colors are basically explained here. So we first go from caution to extreme caution, danger, where we might already experience severe health effects, and then extreme danger, where people might actually then have the risk of dying. And depending on the relative humidity, we might actually reach very high heat index values at much lower temperatures than in more dry conditions. So here the blue line, that would correspond to relative humidity 100%, whereas here this magenta line would be more, say, what we probably typically more experience at normal days, maybe also winter time, 40%. And you can see here to get the same heat index value with 100% humidity, that you would already be here 32 degrees. With much lower relative humidity, 40%, we probably can, or the temperature could be more than 10 degrees warmer. So that's also then very important to consider for the health impacts, and also try to understand this. So in order to get into the dynamics, so I split my presentation in two parts. First part, I want to talk a little bit about European heat waves, and there especially discuss the role of quasi-stationary wave dynamics. Here we kind of consider mainly the dry dynamics. Also use some nonlinear stationary wave model to look into the dynamics. And the second part of my presentation is then focused on Asian heat waves, where we compare moist and dry heat waves. Depending on the location in Asia, we might have a preference for moist or dry heat waves. And as I will show you over the next 20-25 minutes, also the dynamics of them are different. And then at the end, I have a very brief summary. Okay, European heat waves. So here we started out to derive some composite of European heat waves. So we took a standard heat wave index to identify days when we actually have a heat wave, and then average basically over all those events. So that's then basically here the temperature anomaly, which we can see in this plot here. Also that we then have about 4 degrees on average above normal conditions. And then we, in order to actually try to understand this in terms of quasi-stationary wave dynamics, we of course also have to verify that those situations are associated with some large-scale dynamics. Typically blocking events is also already mentioned in previous presentations. And also then here over the area of the maximum temperature anomaly, we also have here this positive stream function anomaly. So trying to understand this in terms of quasi-stationary wave dynamics, nonlinear stationary wave dynamics. So we basically have to make sure that the events we consider are really associated with quasi-stationary waves, and so that they're not too transient, so too fast. So that would mean we would need a relatively high threshold of the duration of the heat waves. But as you can see here in this graph, if we go to say something like 10 days, then we would only have overall 10 heat wave events. So that might give us a very clear picture, but then probably with large uncertainties. If we go to relatively short periods, say only 3 days, then we have about 80 heat wave events, but they might not satisfy the quasi-stationary wave conditions we would like for looking then with our stationary wave model into this. So we tested around sensitivity, and we found that 5 days durations of heat waves is kind of a maximum between those events reasonably well quasi-stationary, and that we get a still reasonable number of, I think in the end was 38 events or so. So that's basically our definition of heat waves we consider here. So we use a nonlinear stationary wave model that was developed by Min-Fang Teng, which the model description, if you're interested in this, is in Ting and Yu 1998 paper. So that's based on the tri-primitive equations, three-dimensional model. So it's also time dependent. So it solves the nonlinear primitive equations for deviations from a prescribed zonal mean basic state in response to zonally asymmetric imposed forcings. As forcings, we take them from reanalysis data, the JRA 55. So we have topography, diabatic heating, and transient eddy fluxes. So that would be our forcings. So the model we run in R30 truncation with 14 vertical levels. So in order to also try to understand the nonlinear interactions involved in those quasi-stationary wave dynamics, we use the so-called factor separation method. So that's a nice way to separate nonlinear effects between multiple forcings. So we can have here the total nonlinear effect between two forcings. We can separate them into individual nonlinear effects and the total effects of nonlinear interactions here. And then we can basically also do this for 3 different forcings as in our study, and then also have basically individual total nonlinear effects of a given forcing, which we then can also basically compute from here. So basically we just need to run our stationary wave model with different forcing combinations, and then this allows us also to really look into nonlinear interactions between those different forcing terms in a very systematic way. Okay, now let's start looking at this. So we took the forcings, diabatic heating, transient eddy, momentum fluxes from the reanalysis data, and also topography, run the model so we can first have the full response to all three forcings simultaneously. So we get here this wave pattern with this quasi positive stream function anomaly over our heat wave area, and then we can also just look at different combinations here, diabatic heating and transient eddy fluxes, diabatic heating orography, and transient eddy fluxes and orography. And you can see here that we can, as I already pointed out, we can more or less relatively well reproduce the observed stationary wave pattern over the heat wave area. And we can already see here that combinations involving transient eddy fluxes seem to be important. We can then refine this with this factor separation method by looking at the total nonlinear response to individual forcings. And again, basically, we see here that we have here, if we only consider transient eddy fluxes, basically here, the best representation of this positive stream function anomaly. If you look here just at topography, then there is not really the strong anomaly, and also if you just look at diabatic heating. So that means transient eddy forcing seems to be the most essential component. Then we can also decompose those forcing components into divergence and rotational components, so which we did here. And we also see, or here we see that especially the vorticity component, so the rotational part of large-scale dynamics is very important for European heat waves. Then we can also further decompose those transient eddy momentum fluxes into low-pass filtered components, high-pass filtered components, and basically those cross fluxes between low-pass, high-pass, and here high-pass, low-pass. When again our stationary wave model just with those forcings, and we see that it's also mainly the high-pass filtered momentum fluxes which contribute to the stationary wave pattern over Europe corresponding to heat wave events. So another thing we did was also looking in more detail into diabatic heating, especially the region in which diabatic heating occurs. If you just look here at this panel here, that's basically the global distribution of diabatic heating. And then we looked at, so in this box here, that's basically our target box, Europe, where we have our heat wave anomaly, and then we looked at different ocean boxes here. North Atlantic, tropical Atlantic, and also here Indian Ocean and Pacific Ocean combined here. So then we can basically run the model with only partial diabatic heating components. So basically we would then only take the diabatic heating in those corresponding boxes here and basically set everything outside to 0 to see how much those regions would actually contribute in the end to European heat wave events. And if we do this, then we see here that especially the tropical Indian Ocean and West Pacific seems to contribute most to this. There's also a little bit here more closely related in the North Atlantic, but it contributes a little bit, but not that much. So it's kind of more here, really more relatively remote for diabatic heating forcing. So I mean, there are also other studies who kind of find variations here, also Indian Ocean, Pacific Ocean, so that they trigger some wave train, which then might affect our weather or climate conditions here over Europe. So this finding is also consistent with some previous studies. Then we also looked how modes of climate variability might impact the probability of heat waves to occur. So on the y-axis, we always have here basically our temperature anomaly, or the probability for this to occur. And then we looked at the Indian Ocean dipole pattern, North Atlantic oscillation, and El Nino index, Nino 3.4. So the blue lines, that's always say the climatological temperature distribution. And if we then just look at those heat wave events, then we can already see that there is some preferences, higher probabilities for positive IOD states or for negative NAO phases. And also here for slightly positive Nino 3.4 phase state. So that's further evidence that also relatively remote areas can contribute to what happens, say, during the summer heat waves in Europe. Okay, that was the first part of my talk, focusing on European heat waves. Now I want to move to Asia and talk a little bit about Asian heat waves. Here, as I already mentioned, we looked also, say, at differences between dry heat waves and dry heat waves. We define, so on one hand, of course, we have high temperatures, but here we have the second condition that relative humidity needs to be below 33%. And for moist heat waves, again, we look for high temperature events, but they have to correspond to times where also relative humidity is larger than 66%. So we can look then here, trends of dry heat waves, trends of moist heat waves. So dry heat waves occur here more, say, northern China, also in this region, as you can see here, whereas moist heat waves occur mainly here over Southeast Asia. So there's already a clear distinction of those two types of heat waves, also the regions where they occur. Then if we also look at those heat wave events and also compute the heat stress index, something similar to what I showed on one of my very early slides. So how much actually this would impact human health also. Then we can see here mainly dry heat waves. We either are in the safe area or might just get into the caution area. With moist heat waves, then that gets also much more dangerous condition, extreme caution or even dangerous conditions. So that's just to point out again that the moist dynamics or moist effects probably also needs to be better understood. So now looking at a little bit more into the dynamics. So here the shading are the temperature anomalies and the contour lines are precipitation. So during dry heat waves in this heat wave area, we basically have almost no precipitation, so it's very low. If we look more at those moist heat waves, then we also have here negative anomalies, but to the north, some positive precipitation anomalies. Then we can look here at geopotential height. So dry heat waves are very much associated with a pronounced geopotential height anomalies, whereas that's much less distinct for moist heat waves. And we can also look here at the wind directions for transport. So that for dry heat waves, that mainly comes maybe from mainland China, whereas here for moist heat waves, that's probably also comes more, or we might have more like a divergent circulation patterns here. Then we can also look at diabetic heating. Dry heat waves have especially some negative anomalies where moist heat waves probably because latent heat release, probably much higher um, diabetic heating anomalies. Then we can also look at Rossby wave dynamics, dry heat waves. There we can see that already a few days before the onset, which would be here in panel C, already we have the start of the anticyclonic anomaly to occur, and then which then intensifies over the following days. Whereas for most heat waves, so the anticyclone might form maybe just one day before, so that's much more instantaneous. So we can basically infer from this that mainly Rossby wave trains might cause those dry heat waves, whereas most heat waves are more instantaneous. And we also looked at SST patterns. So for dry heat waves, we don't really see any distinct anomalies, maybe a little bit warmer here in the Indian Ocean, but it's much more pronounced during moist heat waves that we have much higher SST anomalies here over the Indian Ocean, but also here close to or here in the warm pool area. So that might provide some kind of predictable signal for predicting moist heat waves. Then we also did some climate feedback response analysis. So here we use the CFRAM framework. So we can look at which effects or processes actually contributed to temperature changes. And here we look at the total effect here, above panel for dry heat waves, lower panel for moist heat waves, ozone, water vapor, surface albedo feedback, cloud feedback, sensible heat flux, latent heat flux, surface dynamics, and atmospheric dynamics. And if we look here for dry heat waves in more detail, then we see that mainly latent heat flux and surface dynamics contributed to positive temperature anomalies. So dry heat waves, that's also consistent with the surface dynamics. So we have typically much drier soil conditions, so we have much less latent heat flux. So much more or the heat flux is mainly due to the sensible heat flux, but then just the loss of the latent heat flux basically contributes most to those more extreme warm heat wave events. For moist heat waves, then we've identified that water vapor feedback and cloud feedbacks are much more important. So there we have, of course, more precipitation, at least towards the north. So and also more cloudy conditions. Then we are of course also interested how this might change in the future. So we look at CMIP6 models, two different scenarios. So here on top, first the trend of the dry heat waves in the historical period in the models, which are relatively well reproducing the observations I showed you before. And then we can also look here at the SSP2 4.5 scenario. All those dots area basically indicates trends which are significant, and we can expect, of course, more dry heat wave events and also longer durations. And it's much more pronounced here for moist heat waves. So the conditions during summertime heat waves might become much more worse than during, say, the dry heat wave conditions here over northern China. Then we can also look at the change in the duration of those dry heat wave events. So they kind of increase from about 10 days to 30, 40 days by the end of this century in this scenario. If we look at moist heat waves, there is also much more model spread. But if we look at the multi-model mean, then we also would go from 10 days to something like 70, 80 days. some models we might actually get up to 150 days. And also the season where those events can occur kind of broadens. So more moderately for dry heat waves, but for moist heat waves, that's kind of also goes more into the autumn season much more in the future. Then we can also look at the second scenario, SSP5 8.5. So again, we see here significant trends in the model simulations. Then we can again look at the number of days of those events we might experience. So in this scenario, those numbers also go much, much higher up. So for some models, we might reach almost 200 days in a given year where this region could actually suffer from moist heat waves. And again, if we basically look at the seasonal changes, again we see this broadening, and especially for moist heat waves, that's like very. I mean, winter season is probably still okay, but spring, summer, autumn, there might still be seasons where also, I mean, if we look here at the past situation, then mainly they just experienced this in May. But so in the future, one probably could say in this area here of Southeast Asia, they could suffer from moist heat waves almost throughout the whole year, which is, of course, also from a health perspective, relatively worrying. Okay, come to the end. Just a brief summary. So first, I showed you dynamics of heat waves are nonlinear, especially for European heat waves. Transient momentum fluxes are primary drivers. And we also found that for European heat waves, they're potentially predictable if we consider those nonlinear effects, especially if our models can reproduce them, and also when considering those heating sources nearby and also in remote tropical regions. And one of the points I want to make here, moist and dry Asian heat waves, they have different dynamics. And especially moist heat waves, we probably need to understand much better in order to also evaluate our models better, because the spread of, say, the duration of moist heat waves is very wide compared with the much more narrow spread for dry Asian heat waves. If you're interested in more details, then I'm happy to answer any questions, or you can look up here those two papers in which we published this. Thank you very much for your attention. I'm happy to answer your questions.
There's time for questions. Just one comment to Jacopo. The hand raise button is at the bottom left, but in case you want to unmute, I can let you unmute after a few questions in the room have been answered. Tiffany, please.
Hi, Christian. Thank you for your great talk. It's a great framework to kind of compare and contrast all the different drivers in the same units, particularly the stationary wave model. I wondered if you had any thought about the recent trends in European heat waves. So your first bullet point would suggest it might have something to do with transient eddy momentum flux. What we know from the literature is that the transient eddies are weakening in summer. So have you thought about the connection to trends of European heat waves and the role of transient eddy fluxes?
Not in detail. I mean, we had this idea that we might also apply this to CMAP 6 model output, but then Jian, he moved on to a postdoc position. So, and since then, we haven't really accomplished much. But you're, I mean, you're right. I mean, on one hand, we see this poleward shift in the North Atlantic jet stream, but I think it's probably also still probably somewhat uncertain whether, say, how storms also actually would change, which basically would be the main main component of transient momentum fluxes. So that's, I guess, maybe in order maybe to look into this into more detail, we might have to look at some large ensemble to really identify the signals. And in my experience, it's probably relatively noisy, and we might actually really need large ensemble to identify whether those transient momentum fluxes, how they might change in the future.
Okay, Melinda.
Hi, Christian. Thank you for the talk. It was nice to listen to it. So can we say then that dry heat waves are basically caused by the mid-latitudes dynamics, by the mid-latitudes wave anomalies, and moist heat waves are caused by interaction of mid-latitudes dynamics and tropical dynamics, because the moisture probably comes from the tropics. And I was wondering also whether this bimodality, kind of bimodality you showed in terms of duration of heat waves, whether that is related to these interactions of processes with different time scales or something like that.
What do you mean by modality? This here.
It's not really, yeah, it's not really by modality, but you see that there is a gap between them, right? So
Yes, but these are
yeah.
16 different CMAP models. Some models might just have a higher climate sensitivity, or maybe moist dynamics might be different in those
Okay.
models.
Okay, so it's
So
basically because of the models.
so right now I wouldn't really say that there is really a dynamical origin. So I would probably more say that there might be model biases
Okay.
involved. And your
Okay,
first
but then
question, I'm not sure whether one could say this in such generality. I mean, here, of course, we look in Asia, but I guess in Europe, maybe one could also then maybe try to look or try to distinguish between dry and moist heat waves, and maybe might find that also there just, I mean, there we probably would have less tropical influence, maybe.
yeah.
But so here, we also have to probably consider a little bit here the topography, Tibetan tableau that might also impact on the soil. Probably, I mean, what one of the differences, of course, here is here basically we have here this Rossby wave train, which contributes, which seems to be also relatively important for the dry heat waves, whereas at least for this location, moist heat waves seem to be much more instantaneous or localized. How generalizable this would be, say, to Europe or maybe the US, I don't really want to speculate.
No, I mean mostly this location.
Yes. So
Okay,
Okay, and then Jacopo, you want to unmute maybe? No, we cannot hear you. Yeah, no, not really. You want to write your question maybe? And maybe there is a written question by Jana that I can read for the sake of the audience in the room. Or maybe you want to unmute Jana.
Yes, can you hear me?
Yes, yes.
Yeah, hi, Christian. Thank you very much for this
okay.
nice talk and these two different regions and different heatwaves. My question close to Melinda's question, and I think you already partly answered that this gap in models between autumn and summer season for wet or moist heatwaves is considered to be artificial. However, in my analysis, when I applied for Eurasian heatwaves, where it's more a bit European part, I also found that some models exhibit also longer duration for autumn season. So I was wondering, maybe still some valid dynamics involved. And my question would also maybe relate to what is the role of monsoon, because obviously in future projection, monsoon is assumed to be changed too.
I'm not too familiar with, say, with monsoon, especially in CMIP 6 models, but I would probably also assume that might be very model dependent. So that's, I mean, probably, I mean, from the comparison here of the duration of dry heat waves, moist heat waves, dry heat waves, the spread is much more narrow. So I probably would assume that maybe in CMIP 6 models, the representation of moisture effects, and that might then goes down to clouds also, which we probably know are probably one of the biggest uncertainties in climate models. Probably might be important, and we might just see here the effects of those model biases.
Okay, thank you.
Okay, in the interest of time, maybe Christian, you can answer Jacopo's question in the chat so that everybody can
Yes.
read it. And
Okay.
in the meantime, we thank you for attending this workshop with this interesting talk. And we move on to Duncan Papper, which is in the room, with a talk on the dynamics of persistent heat waves in European summers and impacts perspective. So I will share the screen.
Change slides.
Yeah, it should work.
Okay.
You are the first one, the first lucky guy who was able to use it. I tested very quickly before and it seemed to work. Okay.
In the meantime, perhaps I can say thank you to the organisers for allowing me to present some of the work I've been doing so far in my PhD. I hope, hello to everyone online as well, I hope you can hear me. I hope you can hear me in the back. All good. Yeah, so I wasn't sure whether to include this slide about motivation because I think if there's a crowd, if there's an audience that doesn't need reminding of this topic, it's this audience here. But I thought it's still important to see in a general schematic way, what is guiding, what concerns are guiding my research and my studies. And the main one to focus on is persistence. When probably I think of subseasonal to seasonal weather persistence, and as we know, they are very often linked to severe high impacts on the ground. And so it's in our interest to better understand this weather persistence in summer, get a better understanding of the circulation, of the dynamics in summer, which can also indirectly then perhaps hopefully help improving subseasonal to seasonal forecasting. The type of persistence I'm going to show you now in this talk is, first of all, if I can specify, thinking of persistence from a Eulerian perspective. So I'm looking at the tendency of the weather conditions to be persistent in the same domain over time. And I'm also looking at something that we can term as episodic persistence, which is tied to specific time intervals or episodes where weather exhibits this persistence. Right. So I'm thinking of the dynamics of summer heat extremes in Europe. I do not want to assume that different parts of Europe will have similar, necessarily the same dynamics leading to heat waves. So I want to, it's also probably relevant from an impacts perspective and risk preparedness perspective to think of more of a regional perspective that might help countries and regions better see what the drivers are in their regions. So what I do is I compute an agglomerative hierarchical clustering. I get aerified reanalysis to meter temperature data, in the 65-year period for the summer. I detrend and deseasonalize these values and basically apply the clustering on the normalized anomaly fields. The clustering is basically, it's important for me to take into account the similar temperature characteristics of different regions, different grid cells. So what I do is I compute the clustering based on this region tendency to experience long duration, 3-week in this case, extremes together or similarly. And in such a way you can binarize the time series for every grid point. And then the important element is that I do this clustering using something called the Jacquard similarity, which can also be termed as a distance metric for the clustering. In its most simple form, the Jacquard similarity or dissimilarity is the intersection between two binary time series divided by the union of the two time series. So it's really good, this metric, if I want to compare patterns. And the Jacquard similarity is a measure of co-occurrence of event synchronicity between data points or regions. So I don't even have to have an a priori number of regions that I want. I simply cut the dendrogram at a level of synchronicity that I desire. And if in my case, I had, I think, a level of 15–20% event synchronicity, which was very lax, very generous, and I end up with these 6 regions in Europe. The clustering is pretty robust if I use just 2-week extreme or different thresholds. You always more or less get a region in Iberia, in northwestern Europe. Sometimes the British Isles are separated, but you always have a Scandinavian region. So this is nice to see. And here I can already think of a research question. Okay, what are the regional differences in the dynamics of persistent hot spells? So now, what are these hot spells? How do I define them? I don't call these heat waves, I call these hot spells because I want to think of prolonged episodes of continuous heat. What I do is identify hot spells as continuous exceedances of 1 standard deviation of normalized 2-meter temperature cluster, so field average anomalies. And I allow my spells to begin in May, and to be a bit more generous, not so strict with the definition, I also allow them to end in September. And more importantly, perhaps though, I merge spells separated by up to 2 days, which is, if you think about it, relevant from an impact point of view. If I have a 5-day spell and 2 days later I have another 5-day spell, the cumulative effect on the ground for natural and human systems is still relevant. As you can see, though, this means you get different types of hot spells. I'm not really interested in intensity, I care about the duration. So once you have this, basically you have a whole, I suppose, distribution, but a sample for every region, and you have different durations of hot spells. And what I can do now, this doesn't only allow me to just pick the longer duration hot spells, the persistent hot spells, but it allows me to maybe compare long duration and short duration spells, and then focus on a region. And this can get me to a question like, okay, what are the dynamical differences between persistent and short hot spells? And in this case, the long hot spells are defined as lasting from anything to 12 to 26 days. This is a very generous definition as well, and relatively subjective, but the reason is also to get they're rarer, obviously, than the short spells, and it's a good way to get a higher sample size for the long duration spells. Yes. So what I can do with this is now plot composites that show me the average behavior or the average state of the atmosphere, a specific variable, during these times. Here you have an example for region 2, north or northwestern Europe. I'm showing on the top blocking frequency anomalies, and on the bottom panels, wind speed anomalies at 300 hectopascal. On the left, you've got long spells, on the right, you've got short spells. What you immediately see is that for this region, the long spells are associated with much deeper, much larger spatial scale blocking anomalies, which you can imagine, okay, the associated Z500 anomalies are also probably very deep and big, and they take longer to dissipate, but also a larger wavelength perhaps means more stationarity in the system, so it tends to stay in place for longer. In the wind fields, you see generally between long spells and short spells a similar, at least locally, a similar anomaly pattern. What you do see is that, interestingly, for the short spells, you have significant overall, on average, significant sort of active jet streaks in this region ahead of the cluster, which could hint to also there being more inertia in the system and thereby pushing the weather systems a bit more effectively further eastward. Whereas here, this seems to be absent. It could agree with more stationarity in the system. Yeah, but it could also hint to the fact that this is a composite, and maybe it shows that it's difficult to have a picture. There's multiple pathways that could lead to these long hot spells in this region. Yeah, so that when you composite them, they all don't necessarily agree. I can look at region 1, and something we found interesting, I cannot show you everything, something we found that was very interesting is looking at anticyclonic Rossby wave breaking, frequency of occurrence anomalies. So anticyclonic Rossby wave breaking, for those who don't know, well, is the refers to the irreversible, well in this case, clockwise irreversible overturning of the PV gradient, and these are very often associated with extreme events at the surface. What is very noticeable is that if you look at the difference between long spells and short spells, the long spells have this very positive, frequent occurrence of anticyclonic wave breaking ahead of the region, upstream of the region. You can see a schematic maybe to see what the anticyclonic wave breaking looks like. If I look in more detail at individual spells, persistent spells, you could see very often a pattern like this. It's basically, you can imagine a ton of positive PV anomalies, stratospheric air reaching down equatorward ahead of the region. Very often, but not always, this can break off into a cutoff, but these positive PV anomalies induce a cyclonic circulation, which has the possibility, again, depends on the journey the parcel makes, but if it's very dry, to advect warm air from lower latitudes into this region. If we look at the wind speed, we see also a probably more shifted jet further north. This also makes sense with anticyclonic wave breaking, the dynamics of this, that you see sort of a jet that is pushed further northward. Again, you see, just like for region 2, you see significant positive anomalies of the jet streak ahead of the region, which could also indicate, that in the case for the short spells, the system isn't just staying long enough in the same way, and it's just moving on. And here we don't have this, but this is also due to like the Rossby wave breaking that is breaking the waveguide and contributing to creating more stationarity. These are just composites. One thing that I want you to take from this talk is also that there's a lot of sample variability of long spells. Not every spell looks the same. It seems like the processes that we are familiar that create these hot spells are all there, but in different combinations, sometimes at the same time, sometimes following each other. There seem to be a lot of non-linearities. Here I just give you 2 examples for region 1. For one long spell and another long spell, these are averaged for the latitudinal band from 30 to 50. You can see sometimes hot spells are associated with a very wavy jet at this latitude, and this, in this case, also to a recurrent Rossby wave packet. Sometimes you can have no wavy jet at this latitude. Perhaps the jet is more zonal, further north. You have a time like more calm winds. It's perhaps a more poleward displaced subtropical high, but it doesn't exclude the possibility of there being a wavy jet further north. And then you see anticyclonic wave breaking is occurring. Blocking is occurring at some point at this longitude. But clearly not every time you have blocking and not every time you have anticyclonic wave breaking. You have a long hotspot, 2 minutes. What are you doing? All right. Okay, so we'll move, it's a shame, we'll move from the upper levels to the surface. I wanted to show you these plots we have on the left. So these are cluster average 1 meter soil moisture anomalies. And you have on the left region 1, on the right region 2. You've got long spells and short spells. And this is basically a temporal evolution of the soil moisture from 6 weeks prior to the hot spell to the first 5 days of the hot spell. What is just important for you to see is the very anomalously dry soils in a month and a half before in region 1, leading to the long hot spells. Where this is pretty much, this average tendency is absent in the short spells, which does not prevent the short spells from also having dry soils. For region 2, you see as you get closer to the beginning of the hot spell, there's a slight negative tendency, but the spread is still very large. But you get significant, on average, dry soils once the spell has begun, meaning that there's clearly very intense land-atmosphere interactions going on once the atmosphere gets into a certain state. I cannot go into this because it takes a bit too long, unfortunately, but please come up to me if you've got questions. Final slide before the conclusion. Here I show you, I'm interested in asking the inverse question. Okay, what is the probability of having a 40-day dry soil spell, and then getting a hot spell? Well, you can see pretty much here for region 1, if I've had a 40-day dry spell, I'm slightly more likely to get a long spell compared to a short spell. For cluster 2, it's not really clear. If I have a dry spell and then the atmosphere gets into a state where it can induce a heat wave, it could be either a short or a long one. So there was a lot to cover. I hope I haven't been too compact, but the take-home messages would be that it makes sense to study persistent extreme surface heat by regions, given the slightly different dynamics at play. And it's nice to frame the study in such a way that I'm contrasting long and short duration events that can offer good insights. We saw more specifically for 2 regions. We looked at the upper levels. We very quickly looked, I apologize, at the soils, but we also see some interesting patterns overall. Clearly, soil moisture memory seems to be important for this region, and very strong land-atmosphere interactions seem to be important at these latitudes. And the main limitation in general for this whole study is the small sample size of extreme events in the reanalysis data. If we have time for questions, please do. Thank you very much.
Okay, there's time for one very quick question. Yeah, Cassandra, can you come close to the mic, please?
Hi, thanks for a really fascinating talk. My question was, where you showed the wind speed for the short and the long duration events. Have you tried separating out start days, end days, and then middle days? Because I'm wondering whether the pattern differed just because, not just, but partially because there's a lot more end days in the short sample, and so therefore it's got that wind that moves the thing.
Right, so I've taken this into account, not specifically what you're asking at the beginning and the end, but I'm aware that when doing the composites, I needed to find a way to give them equal weight, because I've got short duration and long duration. So first, for every spell, I do a mean, and then I do a mean of the spells, so I give them equal weight. And still then, you could say, well, you're capturing a larger amount of variability when you do the means of the long duration spells, because they've got more days in them. So what I did, and I didn't talk about it because it wasn't enough time, but when I did the comparison of the long and short spells, I basically subsample 5-day periods in the long spells as many times as there are short spells, so I can get an idea, a more fair comparison. I'm sampling the same amount of variability. I'm just capturing random days during long spells, and then comparing them to the short spells.
Okay.
If that makes sense.
Great. Yeah. Thanks.
All right.
Okay, thank you, Duncan. And we move to the next speaker, who's also in the room, and I will stop sharing.
Ora si registrerà la conferenza.
Okay, the floor is yours, Tanya. Can you go full screen?
Yeah, okay. I'm Tanya Poria from the University of Tirana, Department of Physics, here in the Faculty of Natural Sciences. and I'm going to present the heat waves in Western Albanian lowland, how extreme the heat waves can be. Firstly, why to study the heat waves? In fact, I have studied and I'm doing research on looking the heat waves in the local scale, because the heat waves, besides the extreme precipitation, heat waves are one of the most faced extreme weather in Albania, and we need more research. We need to have more research on heat waves and the extreme indicators of heat waves, in order to better understand the heat waves and their local feature and their local behavior, in order to improve the policies and facilitate the adaptation. Anyway, motivation to make this research, as I told before, is one of the most faced climate extremes during the last decades in Albania, at least during the 3 last decades. And there is a need to quantify the future changes of heat wave related risk, so that we should have better knowledge of the phenomenon. And of course, the heat waves appear in the large scale, but they behave locally. This is the reason why I study the local features of heat waves, and I focused my research on the lowland of the western lowland of Albania. And for the moment, I'm going to present the results only for Tirana city, that is the capital of Albania, and is the most important city. Here lives the more than the half of Albanian citizens. So to study locally the heat wave phenomena, I adapt a local criterion, and after that we use some statistical thresholds and of course a human related threshold. Which are the main points of this research? We used some new definition of heat wave. We made a long-term analysis, 70 years period, and we used different key indices during the analysis. After that, I'm going to make a result of the a resume of the results, and I will present in the last slide that what we are still working on. Let's go to the heat wave phenomena definition. There are a lot of choices, and there is no universally accepted definition for heat wave. And using only statistical indicators of the type that so many degrees above threshold, or it should exceed some thresholds, etc., is not a stable target, or is not a stable threshold. So I use a local criterion after defining the large-scale heat wave feature, and we use also the human factor. Many others use different threshold definition of heat waves. I use the criteria of daily maximum should exceed 37 degrees, the normal human body temperature, for at least 3 days, 3 consecutive days. And after this filtering, we analyzed in monthly, seasonal, and annual basis 4 very important indices: that heat days, heat waves, heat wave duration, and heat wave peak. And what we did firstly, after the CDF of daily maximum temperatures, we have seen that we have, just a moment, please. Just, okay. Yeah, okay, just a few seconds, please. Okay, after the CDF analysis of the daily maximum temperatures for the Tirana city, we have seen that we have more than 16.6% of the days with maximum daily temperatures over 30 degrees. We have 2.6% of the all days for 70 years with maximum temperatures over than 35 degrees. And of course, we have only 0.7% of all the days that have the daily maximum temperatures over 37. That is our threshold for the days that we call a heat day, that is has the temperature of the human body. And also we analyze the days of temperatures over 40 degrees. You can see here, you can see here in the graph that here are the 40 degrees, so only 0.04% of all the days analyzed. And of course, based on the mean based on the maximums and on the mean of the all the daily maximum temperatures, that is 37.7 degree, we see we have two phases behavior of the maximum temperatures, and we can see that we have an I would say a negative anomaly here up to 1986, and after that we have a positive anomaly up to plus 4.5 degree during the last decades. So after for any days that we have 37 degree, we consider it a heat day, and for the data series we have 173 heat days during all the time, all the period, and in some years we have more than 5, and the maximum is up to 15 heat days per year, and we can just okay, we can look at here that we have many years that we have more than 10 heat days per year. Based on the 10 years moving average, we see that the trend of the higher variation is here during the last 3 decades, and we have here many years with very high heat number of heat days. But not all the heat days are considered heat wave. So to have a heat wave, we need at least 3 consecutive days with daily maximum temperature over than 37. And we can look at here that we have in general up to 86 we have 1 heat wave event per year, and after that we have mainly 2, or in some cases more than 2 heat waves per year. But we should highlight the fact that we are searching for 3 consecutive days with more than 37 degrees. Okay. Okay, and after that we have analyzed the heat wave duration. That is, the duration of heat waves is the number of consecutive days after fulfilling the criterion of more than 37, and we can see that we have the mean heat wave duration is up to 3 or 4 days. So the criterion was more than three and more days to have the heat wave phenomenon. So mainly they are observed during the June months, and we have the maximum heat wave duration up to 8 days. And this kind of heat waves are observed during the August, and we can see an increase on the heat wave duration at the late of 80. We can see here a small increase of the tendency, increase in tendency of the heat wave duration. Going to the heat wave peak, that is, the heat wave peak is the maximum temperatures recorded during heat wave. It may be a 3-day heat wave, or it may be a 8 days heat wave, but the peak is the highest air temperature recorded. And for the 70 years period, we have seen that we have 37.6, the minimum of the heat wave peak temperature, and it includes 0.4% of all days. The mean of the heat wave peaks is 39.7 degrees, and the maximum is 42.2, recorded in 1988. And even here in the heat wave peak analysis, we can see that during the last at least two last decades, we have an increasing of the heat wave peak values.
Minute, Tanya.
How many?
1 minute.
1 minute. Okay, we analyzed, we made the analysis in monthly and seasonal basis, and we can see that we have during the last last decades, we have an increasing trend of the number of days with more than 30 degrees, with more than 35, and of course we have a tendency. All the increasing tendencies dates at the late of 80s, and in monthly basis analysis, we have that more the longest heat waves are recorded during August, and the more severe with the highest temperature peaks are recorded in July and August as well. Resume of the results. At the late of 80s, there is an increased number of the hot and very hot days. There is also an increase in the frequency of the phenomena. There is the heat duration varies from 3 to 8, and also the heat waves recorded from 37, the peaks from 37.6 up to 42.2, and the heat wave is a human risk related when the temperature exceeds the 37. Okay, based on the analysis, we have seen that the heat waves became more frequent, longer lasting, and more severe, and the last decades show higher variation of all heat wave thermal extreme indices. And we hope that the study will gain will be a local objective of heat waves and the extremes, and Our research, in fact, is going on with we are working on developing new indices of the heat wave phenomena, more human related, and we are also working for operational atmospheric shapes or signals to use in the heat wave forecast in order to anticipate the future negative impact of the heat waves. I try to be short. Okay, that's all. Thank you.
Thank you, Tanya. Unfortunately, we have to move to our last speaker of this morning because otherwise we won't have lunch. And which is Hassanian Al-Shamarti from LMU. He's in the room. And I will share the screen. So I didn't see it. Okay.
So is it
The
work?
floor is yours. This is working. So this is the.
Okay.
And you can change slide.
Okay.
Okay.
Hello, my name is Hassanin Al-Shamarti. I'm from Iraq, by the way. So, and I am PhD student in Thomas Bernard Group at Meteorology Institute in University of Munich. This is my project of the PhD.
Sorry, but
Sorry,
we cannot see any presentation.
First of all, this is the photo. I think it's good motivation to any research about the heat wave over my country. And this is actually is normal in summer season. You can see everywhere in June, July, August. However, it's most of several days are announced by as a shutdown or a curfew for the people from the government because the temperature is past the 50. So first of all, I need here to identify the heat wave. So I used the Rossby method. Same with Rossby 2015, and I used ERA 5 data for 0.25 resolution, and I identified the heat waves as a 3 days, consecutive 3 days or more with the T maximum and only more than the threshold or percentile of the June, July, August. Here I show in the upper panel the spatial distribution for the unknown temperature. And you see here the temperature is like it's extend to the north. And here it's more connected with the general circulation influence. And in the bottom panels just show the temporal distribution of the event. And here you can see the strong event just occurred in the June and July, and the longer events in the August. So now the main question here. What are the physical drivers of this heat wave event? So from the dynamical framework, I went to the meridional wind, and I used the composite mean analysis, and I found here there is sign of the Rossby wave for the 10 days or about 2 weeks. And this is the Rossby wave. It seems to be vanished after the events of the central day. And also I found here is the zonal wind. It's look like there is the waveguide of the jet stream. And now go to the hydropotential anomaly. I found there is the hydropotential anomaly, anticyclonic quasi-stationary It's embedded in the Rossby wave, and it seems to be grow up in central day. And this is produced the northeasterly wind over the Zagros mountain and over our region. So now that means that we have here the anticyclonic condition. So this is why now I show here the 500 hectopascal with the vertical velocity, and we found here there is the subsidence over the Zagros mountain and over the west part of the mountains. And this is the west part, it's over our region. Here, I assume the air masses, warm air masses, slide down over this region, and this is produced here for downsloping wind over the west part of the Zagros Mountains. However, in this plot, we found there is the breakdown of Shamal wind. Shamal wind means northerly wind, and this is word it's Arabic, and we used in general in this term to explain the wind of this region. So now look like we have the multi-process for the heat waves here, or multi-scenario of the heat waves. So now let's to ask this question: are these events take same manner for the heat wave or not? So now I classified the events and according to the hydro potential anomaly over the Cassidian Sea, and we found there is two clusters of the event. One, it's look like it's most of the event, and it's happened on are happened in the first and early season, and the other events with the low hydro potential anomaly in the late season. So now let's go again to the temperature. We have the same manner of the temperature, and it looks like it's extend to the north and associated with hydro potential anomaly for the first cluster. And however, on the other side, we have the anomaly temperature, like it's confined and just seems to be localized on this event. Maybe this is, we assume this is could be it's by the seasonal influence or the mesoscale influence. That's why we go to the again with the meridional wind, and still we have the Rossby wave sign, and this is still we have the anticyclonic anomaly. However, with the other side, we don't have any general circulation sign. Now, let's see the first cluster. We found there is the NAO index negative associated with the Rossby. That means we have the zonal jet stream here. It's shifted to our region, and could be this is could produce the more meandering of the Rossby. Again, so let's ask about the other events. What the physical driver of these events? Come back again to the climatology of the Shamal. We found here we have the strong sign of the Shamal, and this is when it looks like in June, July, it's very strong. However, when we composite the 4 days before the event for the full field, we found here is the wind actually is very weak. However, we have the anomaly, it's very strong in the negative side. So let's confuse this is how to show the effect of the Shamal wind here. I plot this diagram for the cross section over the our region and with Hawmola diagram. And we found here, for example, if we compare it with the profile of the wind, we see here the breakdown of the Shamal wind for just 4 days, and this is extend to the up and look like it's associated with the general circulation. However, for the other side, for other events, where we have the breakdown of the Shamal wind, it's extend over 20 days and with the low level of the troposphere. So that means this could be a reason it's come or come from the seasonal influence or the climatology, because it's around the 20 days of the events. Now, let's go to the slide. Go to the subseasonal predictability. I selected one event from the first cluster, and I found here there is good predictability for this event around 10 days before the central day. For this phenomenon, for the same day, however, we selected just the members that is captured the event in the upper, and comparative with the truth of the hydropotential anomaly. And we found there is look like it's matching between for the position of the Rossby wave and the pressure system between the truth and the forecast. However, with the other numbers not capture the events, we have look like it's changed the position between the members and the pressure system. And so now we can say we have two clusters of the events. One event, it's happened in the early season, and this is come by the Rossby wave, and also we have the quasi-stationary anticyclonic system, and also we have the subsidence over the Zagros mountain. However, in the late season, we have the breakdown shaman, its main effect of this event. Thanks.
Okay, thank you, Asanyan, for being so concise. You deserve a question. Questions in the room? Okay, there was Federico, and then
You talked briefly about predictability, and so did you check the difference in predictability between the events forced by dominated by the strong drivers and
Actually, I select just one event for the first cluster about the Rossby wave. And still I work on this project actually, because the work with the estuary data time.
It will be interesting to see the
I need to compare it between them and still in order.
Okay, thank you.
and your sorry, I don't know your name. Okay.
Yeah, thanks very much for this nice talk. You showed nicely the 2 days before central day, 2 days after wave train, and then it disappeared 2 days after. I wondered precisely whether it's 2 days after the end of the heat wave or 2 days after the central day. So how long are the heat waves, and how persistent or stationary is the wave that you see there?
Well, it's because this is the composite mean. So here, the central day, I just select where is the highest temperature. So maybe this is the 2 days after, or maybe it's out of the heat waves or in the same of the heat wave, because the heat wave would take about 3 days to the morning. So I can't say actually if this is in the same heat wave or it's past in general. However, I have a lot of plots actually, but I just selected this is a small plot to show because I plotted about 15 days before and 15 days after. In general, we lose the Rossby wave after the events.
Marco?
Yes, I have to.
Yes, please.
Another question about, I might have missed this during the presentation, but concerning like the events in the late season associated with the breakdown of the shaman winds.
Northerly wind, let to say this is maybe easier.
Sorry?
Northerly wind.
Okay. Do you suspect, or do you think that this could be like associated with some dynamics associated with the monsoon dynamics in Asia, South Asia, or African?
The most important things here, we have the sun for the breakdown of the northerly wind for the two cluster of the event. One light is just connected with the general circulation. The other, I assume, is connected with the monsoon. But until now, I don't have any evidence about that. This is just, I assume that. Because I am from this region, I heard about a lot about the monsoon effect on the August and the September.
Okay, if there are no more questions, I would thank all the speaker of this morning session. I would say that we try to reconvene at, let's say, 2 so that we start at 30 past.
And there's lunch outside.
There's lunch outside, and we have the coffee machine. Yeah.
Ora si registrerà la conferenza.
Okay. Okay, so I'm getting started. Thanks a lot for this invitation, and thanks a lot for organizing this event, which seems very timely scientific gathering. I'm presenting some ideas and results that have emerged in the last few years. I'm mentioning some of the people I have collaborated or I have exchanged ideas with, leading to some of the stuff I'm presenting today. So we will talk about blocking events, and we will talk a bit about some conjectures, maybe ideas, some evidences of the very non-trivial mathematics behind them. So,
Hi Valerio, could you please make it a presentation mode?
I am in presentation mode.
No, I can't see that.
Well, I should.
We don't see your presentation mode, so.
Yeah, I am putting myself. Let me try this way. Well, it should be in presentation mode. Okay, otherwise I'm gonna do the non-presentation mode, which is equally good.
It's not a problem.
No, I don't know. I know sometimes there are these issues, but I would just go like this rather than making a bit fuss. Okay, so yeah, no, thanks a lot. So we will talk about blockings. We'll try to relate their features with the concept of instability of the atmosphere, and try to see whether there is something special about the moments accompanying their onset and their decay phase. And I'll try to convince you that one can indeed associate blockings to special modes of the atmosphere, where modes will be defined a bit more carefully in a little bit. And I will say just a few words about detection. So the science flow is the following. Of course, each result comes from history and from some scientific dialectics. So this starts with the PhD work of a student of mine, Sebastian Schubert, where in this case we use a simple two-layer quasi-geostrophic model and try to study using Lyapunov analysis the properties of flows in the occurrence of when blockings occur or not. Then we gathered a lot of idea in an event, a very important scientific event, and of course very important for personal reasons, also for some people in this crowd. There was in 2017 a symposium in honor memory of Anna Trevisan at CNR in Bologna, and that was dedicated to various topics in atmospheric dynamics, including blockings. I had long exchanges with Stefano Tibaldi and others. And this has given me the opportunity to develop this research line. A few years later, we did the work, we published the work with Andrea Grizzun, that is mostly the content of this presentation, trying to link the local properties in phase space and the global properties of the phase space of a simple atmospheric model. This is then sort of has led to other studies. One is trying to understand in more mathematical terms why blockings can be seen as dynamical oddballs, strange features in the atmosphere. And this has led to the PhD work of Chiara Maiocchi, who recently graduated in Reading, and an ongoing work which involves colleagues in statistical physics, as well as Melinda Galfi, where we try to define blockings as statistical oddballs. And there are closely related science stories which involve other people also involved in this event. So we have tried to studying persistent atmospheric features like blocking has led to investigating persistent, let's say, the impact, if you want, of these persistent events like heat waves and cold spells. And this has been work mostly led by Melinda Galfi in her PhD and later works, and also has led to studying extremes in the meridional transport, atmospheric heat transport, and these are led to a paper that was where the first author is Valerio Lembo. So let's try to make a step aside and try to give a broader picture of what we want to talk about. So the climate, as we know, is a non-equilibrium system whose dynamics is driven by the heterogeneous absorption of solar radiation. As a result of this, a multitude of dynamical phenomena appear, leading first and foremost to a reequilibration or a partial equilibration of the imbalance between the energy input and output between the low and high latitudes and the low and high altitudes of the atmosphere. One can conceptualize the process of the interplay between forcing, transport, and dissipation through the energetic analysis pioneered by Ed Lorenz. Basically, the heterogeneous absorption of radiation keeps the system, the atmospheric system, out of equilibrium and leads to the presence of available potential energy. Dynamical instabilities, most typically baroclinic instability, lead to the conversion of this available potential energy into kinetic energy, which is then dissipated. That's the simplest version. So this is the sort of a global picture of the atmospheric dynamics. What is the manifestation of these budgets and conversion and transport properties? Well, it's a very complex multi-scale phenomenology whereby we have features, atmospheric features, on a very large range of scale. And this range of scales becomes even larger when we consider climatic phenomena as a whole. We end up having also a relationship between spatial and temporal scales. So features that are persistent in time tend to have large spatial scales. And today we're mostly interested in things that are in events that have characteristic time scales of few days to say a month, and spatial scales of several thousand kilometers to global. The space, going back to some classic results, the interplay between spatial and temporal scale in the mid-latitudes of the atmosphere, that's what we're going to talk about, can be summarized by the extremely brilliant Hayashi spectra. That's a spectral density representation in wave number and wave number and wavelength, which allows to describe exactly in a very succinct way where the density, the power density lies. And we see that, and this analysis allows to distinguish between propagating waves and stationary waves. So among the propagating waves that you see in the lower panel here, we have all the synoptic phenomenology associated to typical synoptic features, cyclones. And when we look at the stationary waves, so waves where on the average the omega in the K is 0, so these features have longer spatial scale and longer characteristic time scales. And one of the manifestations of this low frequency variability of the atmosphere associated with standing and persisting waves are indeed blockings. Of course, there is much more, but blockings are a sort of a key phenomenology behind this. And as we know, there are many different kinds of blockings. The classification of blockings, the understanding first in qualitative and then in quantitative terms of blocking is one of the key threads of dynamical meteorology since the 50s, at least, from the work of Rex and so on. And this is related to the problem of classifying weather patterns, which has that has become again a hot topic in meteorology as a result of the methods of being able to apply more advanced statistical methods like machine learning and many other related let's say data science technologies. So we have different kinds, qualitatively different kinds of blockings, different in terms of topology of the flow, different in terms of location of the blocking, so the Euro-Atlantic versus the Pacific blocking, and we have also global blocking. So sometimes the atmosphere gets particularly annoyed and features blockings occurring at the same time in the two main regions where blocking typically occurs, that is in the Euro-Atlantic and in the Pacific sectors. So blockings are very fascinating to look at. I would say many meteorologists have a big fetish on blockings, and they sometimes lead to very high impact events. So an example that has literally become a key, I would say a turning point in the study of persistent extreme events is the case of the 2010 heat wave in Russia, which is associated to a powerful omega block and has led, as in a cascade effect, to literally biblical floodings in North Pakistan. And as a result of the preferential advection of water vapor in a very specific and very high altitude region of the planet. So, and at the same time, of course, Russia was experiencing extreme drought and extremely high temperatures. The topic of persistent extremes is, as I said, is a side story, not in terms of relevance, just in terms of flow I'm following today. It's a topic of the utmost relevance, and I think Melinda will talk about this in the next presentation. So I will not dwell more on that. So what is the classical way to try to approach blocking? So traditionally, the first attempts to clarify the nature of blocking come from studying stationary solution of extremely simplified barotropic or simple baroclinic models of the atmosphere, where we have, let's say in the barotropic case, advection of vorticity, or in the case of baroclinic, in the baroclinic case of potential vorticity, and one tries to find stationary solution to the problem, and the stationary solution are typically identified with either, if there is a multiplicity of such solutions, so multi-stability in modern language, we get one solution corresponding to an approximate zonal flow and something very different, which will correspond to the blocking. Now, and this is something that is extremely important and closely related to the development of the Hasselmann program. The idea is that we observe transitions between these different regimes, and the transition is the sort of coarse-grained view on the problem is that the transition is facilitated by noise. And where does this noise come from? This noise comes from higher frequency modes of variability of the system, in particular through synoptic variability. So, and this has been the sort of hierarchical view on the problem. So we have two slow modes of variability, say zonal flow and blockings, and we have some fast processes that facilitate the transition. And so we go from the world of multi-stability to the world of metastability, whereby transitions are possible between competing states. And there are different ways to study the problem theoretically, and there is a huge literature dedicated to understanding as to whether it is possible to find multiple regime of variability of the large-scale flow of the middle atmosphere, of the mid-latitude atmosphere. I always found very fascinating the result coming from laboratory experiments. There is a series of work where in a rotating annulus experiment, whereby indeed this corresponded to a barotropic situation, one could detect the coexistence of these competing modes of variability, one associated to a sort of zonal flow, one associated to a blocked flow, and sudden and sort of erratic transition between the two. Interestingly, the blocked flow had a stronger variability than the zonal flow, and we will come back to this in a moment. So how this representing blockings is a very difficult task, both for numerical weather forecast models and for climate models. And the improvement in this, the improvement in the ability of models to perform forecasts in blockings has been, of course, is documented, but is relatively slow compared to other measures of improvement of skill of numerical weather forecast. It's hard to capture when the blocking will have the onset, and it's hard to capture when the blocking will decay. Whereas during the blocking event, weather forecast is relatively easy. Okay. Additionally, and this might be seen as even more surprising, the improvement in the performance of climate models in representing the statistics of blocking has been very, very modest throughout the decades. So it's very hard for climate models to get the right statistics of blockings. And there are lots of uncertainties as to whether blockings, the statistics of blockings, will increase or decrease or stay the same in changing, in future changed climatic conditions. So in some sense, this points to the fact that these blockings are a really difficult beast. And it's not just through technology that we're going to get what we want. That is a better ability to forecast them and a better ability to represent their statistics. So this is mostly the work I've done with Andrei Gritzun. What we did was taking a model, a simple yet very, very informative and useful quasi-geostrophic model of the atmosphere. It's a global quasi-geostrophic model introduced by Marshall and Montaigne in the 90s and used really a lot in theoretical studies of the atmosphere as a way to interpret actual observations. So this is a quasi-geostrophic model with few layers, and this model is run in such a way that one can get, I will not go into the details, let's say, I wouldn't call realistic, but reasonable climatology, reasonable statistics. Of course, the model ends up being in a turbulent regime, and in this turbulent regime, we have a lot of instabilities. The instabilities of a general nonlinear model can be quantified by the Lyapunov exponents, which describe basically the different possible rates of increase of perturbations along different directions with respect directions of perturbation with respect to a reference trajectory. This is, of course, one could dedicate 1 hour just to discuss this concept. I'm keeping things very easy. Anyway, the presence of at least one positive Lyapunov exponent is one of the, let's say, necessary condition, at least according to some scientists, for chaos. Now, the Lyapunov exponents, in fact, in a model like this one, you have several positive Lyapunov exponents, meaning that there is the dimension of the so-called unstable manifold is large, is relatively large. We have a lot of instability, a lot of ways to technically convert available potential into kinetic energy. And the key dynamical features of the key dynamical quantification of instability are the number of the positive Lyapunov exponents and the sum of the value of the positive Lyapunov exponent, and of course the value of the first Lyapunov exponent. These are global quantities, but there are also finite time, and in fact also finite sites equivalent of those. We focus on the finite time that basically describe the property of instability for a given time horizon. So let's say 1 day in our case, to keep things simple. So then in this case, if we run the model, each day we have an evaluation of the state-dependent instability of the system. So what does our system say? Our system has about 40 positive Lyapunov exponent, and one can estimate on a total of 512, if I remember correctly, degrees of freedom, that the attractor has a dimension, Kaplan-Meier dimension of 89. So it's a very high dimension chaotic system. Now, this system, this model is constructed in such a way that we sort of having blocking is possible, and indeed blockings appear thanks to the boundary condition and the features of the system more or less in the right location. So in the Atlantic and the Pacific sector, they are much simpler and shorter lived than the real ones, but there are things that indeed look like blocking, in the sense that if we use the classical Tibaldi-Molteni detection algorithm, we do find the blockings in this flow. So it's, let's say, it's in some sense Earth-like. An interesting feature is that if you take this model and for a moment you forget about the existence of blockings, you discover that there is a huge fluctuation in the local instability of the system. So this tells you that this system, this simple model, has the predictability of this model depends a lot on the state. So this is a very sort of realistic feature of this model. And just to give you a sense, we have fluctuations in the number of positive local Lyapunov exponents, typically between 30 and 60. So this means that the predictability property of the system changes dramatically from one day to the next, basically, or at least this is, and note that here we are considering perpetual winter conditions, so we don't have, let's say, seasonal effect. So it is a very, let's say, the dynamics and the predictability are very non-trivial. Where do blockings appear in this thing? So the first, a first result is that if you stratify your measures of instability according to the days where you detect blockings, you have that blockings, the days when you have blockings are characteristically more unstable than days without blocking. So the presence of blockings leads to an enhanced instability of the system. And not only, if you follow the evolution of the instability throughout the blocking, you discover that this instability is larger at the onset and at the decay of the blocking. So the idea is the system needs a lot of instability to create these spatial coherent patterns and a lot of instability to get rid of this. And this is connection with information theory, in fact. The fact that blockings are associated with regions when you have of higher instability confirms, first conserves the earlier result we obtained with Schubert in an even simpler model, and observes the conclusions drawn by Faranda et al. In a 2017 paper on observational data, where they used a totally different approach based on the study of the recurrence of atmospheric flow through extreme value theory. Now, so this is already a good, this is an interesting feature. Blockings are associated to higher instability conditions of the atmosphere. Can we sort of make these blockings more real? So here we are using the Tibaldi classification method, so it's a sort of let's say legal framework with a normative framework to define blockings. Is there something more real, dynamically speaking, regarding this blocking? So a way to approach this problem is to take a totally different route. Instead of a local analysis of the phase space, a global analysis of phase space. And we can be helped a lot by the theory of unstable periodic orbits. So chaotic system, the attractors of chaotic system contain an infinity of densely spaced, densely packed, closed solutions, unstable solutions, which are the unstable periodic orbits. And the one can use these orbits to basically describe all the properties of the flow. And these orbits are used not only theoretically, but to understand the features as an example of turbulence in fluid flows. So you can find that, let's say, features of the flow that are associated to exact solutions. Of course, you will never live forever in this exact solution because these solutions are unstable. So the chaotic flow is nothing but it's like being in a pinball game and you are repelled between these solutions. This is actually an exact way to describe, a rigorous way to describe chaos. So this is a case of what I'm showing, the video I'm showing is the shadowing of an orbit of the Lorentz 63 system through the closest unstable periodic solution. This part of the PhD work of Chiara Maiocchi. So in this system, we found 2,600 unstable periodic orbits, which seems a lot, but is in fact a small number. But already this allows us to understand the qualitative features of this highly dimensional chaotic system. And this is very non-trivial. The main result is that these orbits we find are, guess what, extremely heterogeneous in terms of... yes?
2 minutes.
Yes, fine. Thank you. Extremely heterogeneous in terms of dynamical characteristics. So these orbits are have different first Lyapunov exponents, different number of positive Lyapunov exponents, different let's say Kolmogorov-Sinai entropy. This means that the system is non-hyperbolic, and in particular, one finds that the orbits associated with with blocking, so we find UPOs that are permanent, corresponds to solutions where we have a permanent blocked state in the Atlantic or in the Pacific, or both in the Atlantic or the Pacific, have a particularly high instability. So now we understand that indeed there is an ontology of blockings associated with this true exact solution of the problem. Now, the nice thing is that a system, the scary thing is that a system with such a huge diversity in the instability of the attractor is by definition a system that it is extremely hard to model. And the features associated with the largest deviations, the blockings in our case, are those that are hard to model numerically. So the difficulty in modeling blockings is a fundamental problem that emerges even in such a relatively simple model. I stop here. Thank you very much.
Thank you, Valerio. Any questions? Do you have something?
If I may, I have a question.
We have one question from the audience.
For the audience, yes.
Audience first.
Hello, thank you for the good talk. There's something that perhaps I didn't quite understand. I was wondering you could expand on it. You said that the instability is greatest at the onset and then the decay of the blocking.
Yes.
And then the sentence about the longer the blocking, the more the instability. Could you expand on this?
Oh yeah, this is the one. You're right, I didn't mention this. It's in the slide. So it's very simple. Basically, it works, you can think in these terms. The blocking can be seen as a coherent spatial pattern of the atmosphere. To create this coherent spatial pattern, it's very hard, in the sense that you need to create a lot of information. You need high instability to create this object, okay? The creation of the pattern is exactly... Can you hear me?
Yeah, I can hear you.
Oh, sorry, there was an echo. The creation is exactly what demands the highest instability, okay? And it is the most difficult thing to predict, exactly because it's the highest unstable moment, okay?
Okay,
and
thank you.
about the duration is that basically this thing piles up.
Stefano, please.
I was wondering whether artificial intelligence-based forecasting models, how will they deal, or do they have a chance of making better, or will they meet more difficulties in making forecast of blocking in similar conditions as dynamical models at their best possible condition?
So I think it's all about, so the problem is the occurrence of the message is the occurrence of blocking is not just something that is relatively rare, is that also something that is dynamically very atypical, okay? So now the question is if the training allows for the sort of intelligent system to be able to capture atypical dynamical behavior, so things that at all practical purposes obey different equations of motions, where different balances are in action, then they will be able to do this prediction. If not, they won't. So it's like, because the zero approximation to the dynamics in the block case is different from the zonal case. They are two different worlds.
Absolutely, yes.
So the problem is if the system will be able to get that dynamics, which is rarer and stranger and more unstable, and the transition between the two, then they will be able, I think, to understand this in a very non-trivial way, in a very non-explicable way for our words, for our equations, what happens in between. If not, I think they will have hard time, very hard time.
This would have as a consequence that the longer the record, the better the life for the models because
Sure,
they have
yeah.
more chance of getting strange or, if you want, rarer episodes. But on the other hand, maybe the life will be harder if the climate is slowly changing, because then the record is less and less usable as a solid base to make forecasts in a non-stationary situation.
The problem is that, technically speaking, if the model is non-hyperbolic, the dynamics is not robust. So this is a fundamental problem. It's not it's not that if you change the resolution, you reduce the resolution, improve parameterization, you solve this. This is a fundamental problem, and it will stay there. I think there was another question by Jana.
Yes.
I'm not sure whether we have enough time for this.
Yeah, you can make the question.
Okay, I hope it's not going to be long. Hi, Valerio, thank you very much. It was super exciting and very interesting for blocking. So I was wondering, because I look at your PDFs and found that they skewed, and the same result I found for my linear approach. So my question is whether we capture both fundamental property of dynamics, which is both linear and non-linear, or whether it's just coincidence that just by using different metrics and different approaches, we just end up in the same result.
Sorry, I really didn't understand the first part of your question. Sorry.
Yes. Can you please go back to these skewed distributions? Unfortunately, yes, this exactly. The same result we obtained by using linear approach, and we also associated with degrees of freedom, but in standard statistical way. And I was just wondering how it's happened, whether it's coincidence that we have the same result in different approach, or whether it's some fundamental property of dynamics of blocking.
I think it is. I think it has to do with the fact that blockings lead to really a massive. You see it here, sort of. On the average, blockings are, they have a different statistics, like a fundamentally different statistics compared to standard atmospheric conditions. And within blocking, the world of blockings, the variance is even larger. So it's an odd world, and it's a very diverse world. So, so even if you can characterize it as a sort of a separate group, so it's a different group from the average, you can distinguish, and it's also a very sort of diverse group. So I think as a result, somehow a different way, unless your metric really cannot capture the diversity of the circulation, I think that's why somehow qualitatively there are many ways to detect blockings. There are many ways that they tend to give similar results, but of course they are quantitatively different then. Okay, so I think that's why your method still, gives something that is more or less similar to maybe what I'm presenting here. And I think it just gives a sense to the fact that it's a robust feature. It's a very robust feature, but it's a very difficult feature to represent correctly. Okay.
Okay, thank you.
Thank you.
I think we have another question by Yuan Bing, but if you don't mind, you can write it in the chat. And
okay, can you hear me?
Yes, I can.
Okay, my question is that, so you mentioned that you found many unstable periodical orbits, right? And so I'm wondering that if they have a correspondence to the baroclinic instability or the barotropic instability.
Yeah, actually, no, this is a very good question. So we have not done, unfortunately, the energetic analysis of these flows, and this is a very good comment, and we wanted to, and we didn't have the time or the energy to, even if the data are still there. So if you're interested to join forces with me and Andre, you're more than welcome. If I have to bet, I think they're gonna be baroclinic disturbances, because they tend to be very energetic. Okay, so this is my gut feeling, but I would like to be able to answer. But this is an excellent question.
Okay, thank you. Thank you for a great talk.
Thank you.
You can do that, Valerio.
Let me stop. Okay, done.
Thank you. So we can move on to Vera Melinda Gatti. So okay.
We should share the screen.
Okay, yeah. Can I start?
We
Give us a
do not see the
second.
screen.
Maybe here. Okay.
No, aspetta, torna indietro. Lascia Chrome. 1 second, sorry. Because we are not sharing the screen, that's the thing. I don't know why it's not.
Okay.
That's good. Okay.
Yes, so hi everyone, and thank you, Valerio, and to the organizers for inviting me. It's nice to be here, and I enjoy being here. So now that we have talked about the atypicality of blocking, and we have heard a lot about different trajectories leading to extreme events, let's talk about the typicality of extreme events. So it goes a bit into a different direction. But I think it is still something which is there, and it's good to know that there is a typicality of extreme events. So when I explain what I mean by typicality, I usually say what typicality does not mean. So it doesn't mean that extreme events are similar with usual conditions, but it means that extreme events, if they are really extreme, they are similar among themselves. And the more extreme the event is, the more similar are these extreme events with the same magnitude we select. So it doesn't mean that there cannot be different trajectories leading to a certain extreme, like Jacopo and Gabriele presented yesterday. But the point is that there are reasons to believe that if there is a very rare and extreme event, sometimes it is reasonable that there is one trajectory leading to the event, or there is one typical trajectory. Yes, so I started to work on this or on similar things already during my PhD with Valerio, and parts of this work are done together with Gabriele and Jacopo, both presented yesterday. Yes, okay. So let's start. So I'm talking here about the typical of the untypical, and I would like to explain you what I mean by taking the example of heat wave. So very extreme heat waves happen in a certain way. Now, these schematics here is only for visualization purposes. So it's not about which process is most important and which process is contributing, and it's maybe not also complete. But my point is that you get the idea. Okay, so usually, if we have like a temperature anomaly at the surface that is related to a stagnating high pressure system, and then we have subsidence, and we have this positive temperature anomaly. And then we also have clear sky conditions, especially in the peak of the summer, so there's a lot of insolation coming and absorbed by the Earth's surface, so this temperature anomaly becomes bigger. Yes, and then because of this circulation system, there is some warm air advection from the south, so we can even get warmer anomalies. And if we have dry soils, then we have more sensible heat flux, less evaporative cooling, which again increases the temperature anomaly. And then there are the effects of the diabatic heating and so on. But the point is if the system, the atmosphere, wants to realize a really, really extreme anomaly, it needs all these ingredients to realize that anomaly. And of course, these ingredients may vary in terms of location, but to produce something really extreme, you need all what you have, right? A moderate anomaly, on the other hand, can be realized in several ways. So it doesn't have to be related to stagnating high pressure system. Maybe it's not persistent at all, or maybe it's related to a low pressure system. Maybe it's related to the warm sector or the warm front of a low pressure. So basically, we have different ways to realize that. And that's the whole point of the typicality of extreme events. So why is this important? I'm looking here at very extreme events, like with return periods of equal to or above 50 years, 100 years events. And these are high impact events, or but they are still relevant for climate risk estimation, because like they are still frequent enough. And then these typical extreme events are also the most probable extreme events. Thus, if we want to prepare to a certain type of extreme event, we should start preparing for them. So the main message of this talk is that actually extreme events do not have to be always surprising. While they are different from usual conditions, they can be very similar or similar among each other. And this is what I call the typicality of extreme events. And the mathematical background comes from large deviation theory. Now, I will not go into detail in large deviation theory. I would take a bit of a more dynamical system, a more like trajectory-based perspective, and I will try to explain it to you what I mean. So, climate extremes, if we talk about certain properties like typicality, then this typicality has several layers, right? So we might have some typical spatial patterns. There should be also a typical temporal evolution. And there are certain types of physical processes which are involved in this typicality. And if we have a very extreme event, these processes are more connected to each other than usually. So if we have all these typicalities on different levels, then we can talk about the typicalities of trajectories in the phase space. And this is connected. So this typicality of trajectories is connected to the so-called instanton hypothesis. Now, there are people who don't like this concept, but I think it's a quite useful concept to understand things in an intuitive way. And the instanton hypothesis says that trajectories in the phase space leading to an extreme state of the system concentrate around the typical or most likely trajectory, which is then we can call it the instanton. Okay, so for example, if we have a very simple two-dimensional system, only x and y, and this is an extreme state, then this would be like one trajectory leading to that extreme state. If we would observe another trajectory which leads to a similarly extreme state, then maybe we would get something like that, a different trajectory, but with certain common properties with the first one. If we would look then on many other trajectories, we would see that they all differ from each other, but there is definitely some common or most probable trajectory. And so this most probable trajectory would be the instanton, which is symbolized by this blue line here, or sometimes, depending on the framework we use, it refers to the common initial conditions, which then kind of cause this extreme event. But the point is that this instanton trajectory is not a real event, right? You would never observe that. So you would always observe something which is similar to it, but fluctuates around it. But it kind of attracted extreme events, and it makes them becoming similar to each other. And in our work, we looked at the typicality of spatial patterns and the certain typicality of physical processes. but mainly we focused until now on spatial patterns. Okay, so I would like to answer a few questions in this talk. And the first question is whether there is a typical way to realize a large and persistent local temperature anomaly at the surface. And if there is, then what is this typical way? And then another question, whether there is a typical way to realize a large and persistent temperature anomaly around the hemisphere. So maybe it's not like completely hemispheric, but it should be something large. And then another question I would like to answer is whether there is a typical way to realize a large and persistent geopotential height anomaly around the atmosphere, and does these two differ from each other? So let's start first with the local case. And we have used here, because we want to study very extreme events, so we have used 1,000 years of pre-industrial control simulations with the MPI-ESM model. There is no climate change signal into this, just the control simulation pre-industrial. Yeah, I mentioned. And we look at an extended summer. And we select a large temperature anomaly in time at this location here, marked by the green dot. So I selected every temperature anomalies at this location over 30 days, which are on average 4.5 Kelvin, or around 4.5 Kelvin, and this is the composite over those events, so I have maybe 20 or 30 events. And this is what I get. And what you see is that even if I select a local anomaly, I obtain a large anomaly pattern in terms of temperature, so which tells me that during these very extreme events, the correlations among these grid points are stronger than usually. And this gives me a typical spatial pattern. And what we also observe is that the 500 hectopascal geopotential height anomalies are also very strong, although I select the event only based on the local temperature. So, and this tells me that these typical patterns can be found for several variables, and that during these very extreme events, these variables are more connected with each other than usually. So then I also looked at larger, so I took also larger anomalies, and I averaged over larger anomalies as well. And so if these events are really like, if we have a typical pattern, that these spatial patterns shouldn't change by taking larger events. And it is indeed not changing much, so we get the same pattern. Now you might wonder, okay, so this is a composite, and we heard a lot that one should be careful with composites, so how do individual events look like? And I would like to show you only a few examples. So of course, during individual events, there are fluctuations. The atmosphere is chaotic, right? So you will never get the same state. There are fluctuations, but you definitely have some common properties. And these patterns identify those common properties. So now let's expand the picture a bit, and let's look at the larger scale anomalies. And this is how the larger scale anomaly looks like. And you see that it is somehow related to large scale wave patterns. And this would be then an estimate for the instanton, right? So although I don't look, I don't consider the trajectory, but it is an instanton estimate averaged in time. But then, for example, what happened during the 2010 Russian heat wave, yeah, I forgot to mention that the aim was here to study the 2010 Russian heat wave, but you probably realized based on the location. So during the 2010 Russian heat wave, we had something like this. And this would be then one realization of the instant, right? And then we looked also at patterns in other locations. So we wanted to study the 2021 Western North American heat wave, and we looked at it in the same model simulations. And we looked at the patterns corresponding to all these grid points here. And what we obtain here is that you see that usually these local temperature anomalies are related to large-scale circulation anomalies. The circulation anomalies might be not that large in case when you have these more like high latitude blocking type of circulation, but at the lower latitudes you have you see these anomalies which look like waves. So the red dots here are intended to show a bit the similarity among these events, and they show where the maximum high pressure system is located in the individual event I have selected. And you see that there is some variability, but they are all focusing around a certain location. So these patterns seem to be quite similar to each other. And now we wanted to test like a more severe definition of typicality. So we wanted to check, or I wanted to check, whether by selecting more and more extreme events, is this similarity increasing. So here you can see I'm increasing the temperature anomaly. And again, the red dot, which you cannot see that super well, but they show you the center of these geopotential height anomalies in the individual events. So what we see is that the more extreme the event, the more concentrated are these dots, right? And the more similar are the events. But what we also see that these very extreme events, in terms of patterns, doesn't look super different from moderate events, right? So it's not like a black swan or something. So it's like more like a fat white swan, maybe. So it has a large intensity, but the physical processes are known also from the moderate events. So it's not like something freaky in terms of physical processes. And then this is actually a different study which we did with Gabriele, but there is one point which is, I think, somehow related to this typicality, or more precisely to the fact that connections between different variables become more extreme if we go to more extreme levels. So what you see here basically quantize of, so here we were looking at the connection between persistent North Atlantic jet anomalies and precipitation extremes over this Mediterranean region. And basically what this weird plot tells you is that the more extreme the jet event and the more extreme the precipitation event, the stronger is this connection among these two variables. And what we can do is also, like, if we have identified this typical pattern, this typical model events, we can compare those events with the actual observed events, right? And then we can say if an observed, the 2021 Western North American heat wave or the 2010 heat wave based on reanalysis would fit to this ensemble of typical events we have based on the model. And what we find in case of the events at which we have looked is that in terms of the large-scale circulation pattern, these very exceptional and record-breaking events are indeed would be the typical events. This doesn't mean, of course, that global warming is not making these events more frequent, and they are not becoming, in a way, don't have more impact because of global warming. Okay, and as I mentioned, we looked only at part of typicality, I would say, but there is this recent study by Robin Noyer from Paris who did an even more thorough analysis, and we looked also at the typicality in time, so the more thorough analysis of trajectories actually, and he did it for the for European heat waves, and it confirms our results as well. Okay, so let's go to my second question. So let's see whether there is a typical way to realize a large and persistent temperature anomaly around the hemisphere. So what I do here now, I look at the, I'm interested at the zonal fluctuations of temperature. So not really at the cases where the zonal cases where maybe there is a large temperature anomaly all over the hemisphere or something like that, but more like on fluctuations. And this is why I computed the zonal file.
You tell me 7.
Okay. Okay, no, but it's fine. So, zonal variance of temperature, and I'm showing here what I obtained for a certain latitude, latitude 55, and I take the same model simulations I mentioned before, so these MPISM control runs, 1,000 years summer. And what I did is that I averaged these zonal anomalies over 7 days. So also in the previous case, I didn't do any filtering or a low-pass filtering or anything. So it was just averages. I now only compute the zonal variance and I average over time. So, and then I select the 20 largest values to see what I obtain. But these are very loose conditions, right? So it's a very loose selection. So why should I obtain anything? Let's see if something comes out, and this is what comes out. Now this, of course, the shading is the temperature anomaly. Now I'm looking at 7 days average, I mentioned. And then the contour lines show you are increments of 10 hectopascal geopotential height anomalies. And what I clearly see is that I have these two high geopotential height centers, which are then somehow related to these high temperature anomalies. Now I wanted to have a bit of a feeling of how similar are these the individual events I have here. So I'm showing you then the location of the maximum geopotential height over these two regions, and you see that this is a bit more spread than in case of the local events, right? Because like I have like a hemispheric anomaly and I have more degrees of freedom, so it is more harder to obtain something super similar. But you still see that many of these dots are concentrated in a certain region. You also see that some of the events actually where the geopotential height anomaly somewhere completely in a different location, so that could be actually a different pattern. But let's take a bit of a closer look. So here, for example, like I looked at these patterns which give me then this event, and here I have like the increment is 50, so this is actually much larger geopotential height anomalies than there. But so you see that sometimes these individual events are very similar to what is going on here. It's just that it is a bit more messy, of course, because it's one event, it is more chaotic. And then sometimes they look very different. So I can have a high pressure system over Eurasia, but maybe a low pressure system over North America. So then I counted the cases where I have in these two regions at the same time high pressure systems, or when I have only one of the regions or none at all, and this is what I get. So I have from these 20 events, 13 times I have a high pressure system at the same time in these two regions. So we also have these other cases, but there is still a tendency that one pattern kind of dominates the other patterns. Okay, so now let's select these events a bit differently and let's look at the zonal variance of the geopotential height anomalies instead of temperature. And so we do the same, but then we get a different pattern. And this pattern also has these two geopotential height centers, but there is also larger variability. So if I do the same what I did before, and if I look at the individual events, which then give me this composite, I sometimes see very similar patterns, and I sometimes see different patterns. And then again, I counted how often I have in these two regions concurrent or these positive geopotential height anomalies, and it is a bit less, but still in half of the occasions I have in both of these regions a positive geopotential height anomaly. So things are more messy, but there is still something dominating the others. And it's just interesting to compare these two patterns. They kind of look like the opposite, right? So, but still different. Okay. So I would like to answer now the questions I asked. So is there a typical way to realize a large and persistent local temperature anomaly? Yes, these large and persistent temperature anomalies are related to large-scale circulation patterns. The more extreme events, in case of these local events, so the more extreme the event, the stronger is the typicality, and several record-breaking heat waves are actually typical events. So is there a typical way to realize a large and persistent temperature anomaly around the hemisphere? And this is definitely more difficult, but there is a preferred or most probable hemispheric pattern explaining these events. Is there a typical way to realize a large and persistent geopotential height anomaly around the hemisphere? Is again more difficult, but there is still a certain pattern which is more frequent than the other patterns. But I think it's interesting that if you look at surface anomalies, you have also a more consistent geopotential height anomalies. Like kind of the surface anomaly kind of fixates a bit your geopotential height anomaly. Yeah, and I think this is enough. Yes, thank you for your attention. By the way, these are like the second part I show you is preliminary results, so might not be everything super clear.
No problem. So thank you. Any question? A lot of questions. I think we can go with 2 questions. So,
yeah, maybe 2 questions from the room and one.
So one from the front and one from the back of the room. Who first? Yeah. Okay, you can go.
It was a really nice.
No, wait. You later. Sorry.
Okay. It was a very nice presentation. I think it was more or less convincing. I guess one thing I would wonder though is, yes, while the high pressure is clearly there when you instantaneously look, but leading up to the event, it seems to be very different. 2021 Pacific Northwest heat wave, my colleagues in Chicago suggest it's from an upstream cyclone that fed into a block, whereas it's a more classical block, for example, in the Russian heat wave. So, I mean, if you look backwards in time, how typical is the event? And then secondly, I don't think you've explained why those regions are the typical regions. That's the million-dollar question. Why wave 2 in parts 2 and 3? Or wave 7, like we heard from Kai? That to me is the real question. Like, do you have any thoughts about that?
Yeah. Yeah, so as I mentioned, like we did this typicality analysis only based on the spatial patterns. We didn't look at the evolution in time, like what you mentioned, that there was something. I think there's always, so this typicality also not like super, it's not perfect. So there is never things never happen exactly the same way. So there is always some fluctuations. Sometimes you have more fluctuations, sometimes you have less fluctuations because everything is very heterogeneous. But the point is here to find out which are these common properties. And then to see how useful they are, and then to go towards, okay, let's look at the differences. But we didn't look at this, the typicality of the evolution in time. What I mentioned, this study, Robin did this for heat waves over Europe, but not for the Northwest American heat wave. But so definitely, like things are never perfect. So there is certain aspects of typicality, and maybe other aspects are then different. Then, in terms of why I have this pattern, I don't choose this pattern. This pattern just emerges. I mean, my I'm trying to select something based on as less as possible assumptions. So I just took the zonal temperature anomaly or the geopotential height anomaly, and and then I took large averages, and this is what I get. I don't know why, but in case of the temperature pattern, I suspect that this is also somehow related. That if you really want to realize a large temperature anomaly over the Earth, over the hemisphere, you really need those large continental regions. So you really have to accumulate a lot of heat. And where can you accumulate better heat than in the quite over these large continental regions? So this is just one assumption for the temperature pattern. But yeah, in case of the geopotential height, it looks like this high latitude blocking are super important to realize this large geopotential height anomaly. But why exactly in those regions, I don't know yet.
Yeah, and following this idea of common trajectories to extremes, so what do you think are implications for predictability? I think it's really interesting because this suggests that you would have maybe better predictability.
Yes, yes, and this is also something I plan to do in the future, like to see, okay, so we have this typicality, but is this really useful? So can I really extend the predictability of very extreme heat waves? Are very extreme heat waves better predictable than less extreme heat waves? Because you can kind of track this typicality better in time. And that would be one of the challenges, to detect then what kind of sources of predictability emerge from this typicality, or does anything emerges at all, or is just something nice but not useful in this sense. So, but this is definitely something interesting, and this is like the way forward, like for me. Yeah.
We have another question online from Valerio, I think.
No, it's Christian.
No, it's Christian. Okay. So Christian, please.
Okay, really quickly, because you almost answered the question for Tiffany already. Can you hear me? Can you hear me?
Yes, yes.
Yeah.
Yeah. No, I was wondering, knowing the typical trajectory or pattern, it is the same about the temporal evolution. So how could you use the methodology to learn something about how it builds up, so about the temporal evolution? So, I mean, do you know ways how to explore more the temporal evolution, and what are the dynamics behind establishing the pattern?
Yeah, I'm not sure if I understand your question correctly, but in my mind, like, it would be possible to select these very extreme events, select their peak, and to track back their evolution in space-time. Like to see in which regions and on which time scales does one get something similar, something typical. Is this useful for predictability? But there is a way to do that. I think one can do it with very simple metrics. One can do it with machine learning, and it would be also nice to compare different approaches to detect these trajectories, and then to see how useful they actually are. I don't know if this was your question, or did I went into a totally different direction?
No, kind of. I was just wondering whether your methodology could be used to more explore the trajectory in time, but you kind of answered it. So yeah.
It could be extended, like the methodology I used until now, not really, because that is only detecting the similarities in spatial patterns. But I think there are quite simple ways to extend to do this space-time detection of typicality.
Okay, thanks.
Thank you.
So thank you, Melinda. We have a comment. Yes.
Valerio, can you unmute? You wanted to make a short comment.
Can you hear me?
Yes.
Yeah, sorry. Just I wanted to say just one thing, that the story Melinda Sterling is being confirmed in a forecast sense in a recent paper by Fisher, where they studied the onset of the heat wave of the Northwest Pacific heat wave. So basically, what they saw is that by boosting the ensemble, it goes preferentially in the right direction of building up the heat wave. So the dynamical typicality is the existence of a path in phase space, in this very high dimensional phase space, is confirmed when you perform forecast. So that's actually quite a good sign. So it's not only a statistical feature, it seems to confirm that there is a dynamical link. So you go into a very special region of phase space, and then you follow the highway leading you towards the heat wave. It's very unlikely to enter the highway, but once you are in the highway, you're going to get there, basically. It's a conditional probability. Okay?
Thanks, Valerio.
Yeah.
Valerio. So the next speaker is Pascal Yu. I think he's online. Yes. You can unmute.
Yes. Can you hear me?
Yes.
Okay, good. Should I share my screen?
Yes, please.
Okay. Where am I? Where is PowerPoint? I can't see my PowerPoint.
No, we don't see your PowerPoint, so
You may just share the desktop and then you go wherever.
Okay, let me generate see a PDF then. Sorry about this. I thought that my PowerPoint was ready. Okay, it doesn't work. Let's try again.
if you want, we can share it from here. If you prefer, just tell us.
Okay, I try to open the PDF file. Things seem to become extremely slow suddenly on my computer. Okay, so let me see if I can share this screen, application. Why doesn't it, so it doesn't want to show anything that's, okay, yes, here.
We have it here just in case.
Can you see something now?
Yes. It's not full screen, but we can see it.
Okay, let's see if I can do this. Okay, is it full screen now?
Not yet.
Not yet. But I think it's okay.
And now is it
okay?
Is it full screen?
As it is. So.
No, it's not full screen. Actually, you're not seeing my screen.
Okay. No, we can see your screen, so you can start.
Okay, can you see? No, it's not shifting now, is it?
No, it's shifting. It's fine like this. You can go. I think.
Okay, can you see the second slide?
Yes.
Okay, good. Okay, so let's go back. So thank you for your invitation. I'm very sorry that I cannot be with you. So I have the teaching, this is my teaching semester, so it's hard for me to travel. So I'm going to speak about the anticipation of major heat waves by using rare event methods and to design storylines or of events. So it's really a follow-up on what Melinda just said, which is a follow-up of what Valerio said right before. Okay, so the general motivation. So can you see the second slide?
Yes.
Okay, good. So the general motivation. So I will just state the mathematical hypothesis or questions. So we have a physical system X with complex dynamics, everything that has been discussed before. We have partial, which means partial finite observations of X, which I will call f of X. And we have observed a record value of observations, which I will call m hat of X. Okay, so this is very similar. So this is another way of putting notations on what Melinda said before. And the questions are how to obtain the maximum possible but potentially unobserved value of f of X. So something that is higher than m hat. What are the precursors of m hat? And is m hat affected by climate change, and how? So we try to answer those questions on one case study. Okay, so there's a practical motivation here. So let's go back 20 years ago. There was a major European heat wave, which had a probability of less than 1,000th, 1 over 1,000, a very small number, which is still a record for summer temperature over France. Okay, so if we want to study the physical properties of such an event, we need to have a fairly large sample of similar events. Okay, so more than 1,000 years, and we don't have enough observations to provide enough samples. Okay, so to some aspect, such events can be outliers for extreme value theory. This was shown by a paper by Eric Fischer this year. So in a way, we are dealing with events that escape a lot of statistical descriptions of extremes. Okay, so how can we do with, so let's go back to the original framework. We have a dynamical system, X, which can be written with this type of equations. We have a scalar observable, T, let's say temperature of the system. So T is some function of the state of the system, and this can be a complex function. So, and I will assume that T is some average. Okay, and the question is how to simulate trajectories of the system X that maximize an average or seasonal average over a period of time, let's say P. So P days of the observable T. Okay, so P can be 90 days or 92 days for the summer, or it can be a shorter time interval. And we want to simulate trajectories of X for which the trajectory, the probability of having a trajectory that has an observable over some high threshold is larger than some threshold probability. So we are dealing with a low probability event. So the unconditional probability can be very low, but we want to find trajectories for which the probability of having high temperatures would be high, so conditional to some initial conditions or to some observation. Okay, so now let's go to some more notation. So we will call the extremes, assume that of being around A or in A is very small, okay, 10 to the minus some large number. So this in conditional probability could be very hard to estimate due to the lack of data. So this has been, Valerio just discussed this a few minutes ago. And the first challenge that most climatologists have to answer is, what is A? If we set a low probability, what would be A? What would A look like? Okay, so that's the identification of what is the extreme. What is the extreme in all phase space? The second challenge is to make a forecast of A. So identify initial conditions that are leading to A. So that's if we know what the instanton is, so we want to identify where does it start. Okay, so how to do this? So there are several ways of doing this. There are rare event algorithms. One way of simulating rare trajectories of the system leading to an extreme. And Ragon et al. Pioneered a way of doing this by simulating a simple model. So there was quite a spectacular paper. And the general framework for rare event algorithm is large deviation theory that Melinda and Luca and Valerio mentioned. And there is a simple version of this, which is ensemble boosting, that Valerio just mentioned. That's used by the team at TTH Zurich. And the requirements for this type of approach are models. You need models which are either physical or statistical. So we are going to deal with models. And the end uses are the anticipation of worst case scenarios, like the so-called storylines. And the other aspect would be, how does climate change affect this extreme state? And that's the type of question that we try to address for the attribution of extremes. The second challenge is to estimate the probability of reaching the extreme, and especially the probability of reaching the extreme sometime before. So that's the challenge of forecast of the trajectories leading to an extreme. But I might not discuss this today. Okay, so now I'm going to discuss about a cost-effective framework to simulate such extremes. And the cost-effective framework is based on analogs or recurrences of the system X. So I will call them analog of circulation to simulate temperatures in the mid-latitudes. So I'm going to use a stochastic weather generator as a climate emulator for temperature extremes, and we'll see how this tool can help address challenges of simulating worst cases or the impact of climate change. And I will focus on one or two case studies, depending on the time it takes to explain this. How do we do this? So we are going to adapt an analog stochastic weather generator, which essentially reshuffles analogs of circulation with there is some art in doing this. I will explain the art with weights towards the highest temperatures. So how does it work? So the analogs are fairly rudimentary. Analogs are fairly rudimentary machine learning approaches. So let's assume that we are on one given day, let's say the 29th of November 2023. We have some, well, so let's say, let's assume that it's the middle of July 2022, because this map is not realistic for today. Let's assume that on the 22nd of July 2022, we have this type of circulation pattern. So the lower map is Z500, and the upper map is a temperature map. We are going to look for similar maps in the past or the future, of Z500. Okay, so we have similar maps. We have dates in the past, and we can associate a temperature map to those Z500 maps, and we can compare the temperature maps to the map of, let's say, the 22nd of July. And we can make samples of those maps, random samples, in order to build trajectories. How does it work? Okay, so we start at T0, okay, the 22nd of July 2022. We look for analogs, which are the red dots of the starting date, and I choose one at random, okay, this one. Okay, so I move forward because I know what will be the next day for that day. So it's T1, and I pick one of its analogs at random, and then I move forward, and then this allows me to generate a random trajectory. Okay, so this is the basic flavor of the stochastic weather generator. What can I do in addition? I can put a rank on the random selection, so I can give more weight to the analogs I will select according to their temperature. And in order not to be too dependent on the units of temperature, I'm going to put a weight on the rank of the temperature of each of those analogs, so that I'm going to select more warmer and warmer analogs. The other thing, so that's the other piece of art that is useful for this stochastic weather generator, is to put a weight on the calendar date of the selected analogs so that time moves forward. Okay, because we don't want to be stuck in the middle of the summer, because that's cheating. So the summer starts somewhere in June, ends somewhere in early September. And if I want to simulate a warm season, it has to start in the beginning of the summer and end somewhere at the end of the summer. So that's where this weight is very important. Okay, so we choose those weights, so those values. So it's the trial and errors. So let's do this. I will skip this. So this is the procedure that we use. So we can simulate 30-day events, 60-day events, 90-day events, or 15-day events. Not so there's a choice to be made on the length of the event, because if it's too short, then the trajectories tend to look alike, so it's not very useful. So the rare event algorithms work when they consider long-living events because of the separation of trajectories. So that's an idiosyncrasy of this type of algorithm, but so that's why we cannot simulate events that are shorter than 2 weeks. 2 weeks would be the limit, in my opinion. Okay, so this is a Markov chain for which I bias the choice towards higher temperatures. Okay, so I will skip this. So there are parameters to be optimized, but let's go. So let's go for a case study. So let's go for this emblematic case, which is the Paris Olympics, which have not occurred yet. So we are going to generate to try to evaluate to what extent we can get a very warm heat wave next year. Okay, so we don't know what next year will look like. We just want to see if something like 2003 is likely, and can it be worse than 2003? And what are the atmospheric patterns during such a worst case heat wave? Okay, so just to start, the Paris Olympics in 2003 will occur between the 26th of July to the 11th of August, which is by some strange coincidence. So I wonder if anybody had anticipated this, which is the apex of the temperature seasonal cycle in France. I don't know if the guys in the Olympic Committee were aware of this. I don't I didn't think that that was a breaking news, but well, they made this strange choice. And the question is, can the record shattering event of 2003 be broken in next year? So what are we going to do here? We are going to consider TG 15 days, which is the maximum, the warmest spell of 15 days in June, July, August, actually, in the Paris area. So it's a small region. And we are going to consider 4 SSP scenarios of CMIP 6 between 2015 and 2050. Okay, because 2014 just sounds good, but it could be any actually a heat wave could occur. If it occurs next year or the year after, maybe it will have different consequences on human health, but climatologically it's almost the same, and there's not too much of a divergence between 2015 and 2050. And we are going to compare those with the historical simulation between 1950 and 2014. And let's go on the next slide. So on this very complicated graph that I can see only partially because GoToMeeting added a lot of things on my screen. You can see temperature variations. So that's the maximum average temperature for 15-day periods over the Paris area. So the green line is what we see in the historical simulation of the IPSL model, and the colored lines are the variations in 4 different SSP scenarios. Okay, so it goes up and down. The dots are the observations for the Paris region, and the record value is still in 2023 the 2003 is still the record value now, so it's the highest value. And the triangles are the values of the average temperature values during the previous Olympics, so which were at different places, different seasons. But the only Olympics that reach or exceed the values of the heat wave in Paris are the Tokyo Olympics. But during the Tokyo Olympics, there was nobody in the streets because Japan was there was a lockdown in Japan. So the athletes suffered, but not the Europeans because there were no tourists. Okay, so now if we go to the future, we see that well, this record value can be exceeded in some scenarios, and the question is, can we do even worse than this? Okay, so let's go next. So we performed ensemble simulations with by using the IPSL model. Well, we did this with all CMIP 6 models, of course, but I will give an example with the IPSL model, which I like because I work at IPSL. And let's look at one of those, let's say the second one, so the C box plot. So those are simulations of with hundreds of so those are hundreds of simulations with a stochastic weather generator, which is initialized on the warmest TG15 that is found in the IPSL model. So it's initialized on the first day of the orange dashed line, so which is different, of course, which depends on the scenario itself. And the red or the brown horizontal line is the observed value in 2003 in Paris. Okay, so we see 2 things on those diagrams. The first thing is that it's close to impossible to reach 2003 values in the 20th century with this approach. But if we start if we allow analogs to be picked between now and 2050, then not only it's possible to reach or exceed the value of 2003, but this is almost typical, and it's you can exceed this value by a few degrees. Okay, so I will shift because I'm getting late. Now we can look at the atmospheric circulation during those simulated events. So on the column of yes, 2 minutes.
2 minutes, yes.
2 minutes. Yes. I'm almost over. This is okay. So on the left, you can see the atmospheric circulation. So that's sea level pressure and sea level pressure anomalies that are observed during the most extremes that are simulated with the IPSL model. So that's what the IPSL model says. Between now and between the beginning of the 21st century and 2050. And the events are slightly different, but you can see an anticyclonic pattern on the eastern side of France over Scandinavia, and in some and there is a slightly low anomaly, which is unstable. Actually, this low anomaly moves quite fast, and this is the type of anomaly that that conveys warm air from North Africa into Europe. So that's really an addition of two phenomena. So that's the blocking phenomenon that was discussed right before, plus depression here, a low pressure system that moves, that is very short-lived, but brings additional warm air out of North Africa. And this is, so I cannot see what those maps because of GoToMeeting, but on the right side, this is what we see with the simulation, with the stochastic simulations by resampling. And if I showed a movie, you could really see that temperature starts to be warm because of the anticyclonic circulation, and then suddenly this low pressure system develops and invades and disappears, but brings a lot of warm air suddenly during the heat wave. So that's a cutoff flow. Okay, so we did this for all the models, but I will not detail this. And I will, since it's only 2 minutes, I will go to the conclusions. I will emphasize the role of the atmospheric circulation in the generation of those major heat waves, and this is very coherent with what what Melinda and Valerio showed previously. This is not a forecast of the Olympics, of course. This is just a way of anticipating a worst case scenario during the Olympics. And if we want to do an attribution of something that has not happened before, we can see that the 2003 record can be exceeded fairly easily with analogs. So that's the preconditioning leading to heat waves. So analogs in 2001, 2050, but hardly with analogs in the 20th century. Okay, so perspectives, can we make a forecast or prediction of this? So this means that we need to estimate what is called a commuter function, which is the probability of reaching an extreme spell of 15 days sometime before. So this can be done fairly easily. And how to reach the upper bound of maximum daily temperature, which is a separate question. Here we are dealing with the average of temperature. So temperature, since temperature is resampled, so we cannot get larger daily temperatures than what is already in the database. It's just that the average can be much higher than what was already in the database. But we've been working with analogs on how to find the upper bound of maximum daily temperature, and we're not there yet. But okay, and this is the end. So I thank you for your attention, and I can take a few questions.
Any question from the audience? Okay, I have a question. Do you think that this approach is somehow exportable to the prediction of moderate extreme events? So not such a real extreme event, but something in a lower percentile, let's say.
Well, yes, it depends on the type of extreme event. So I was saying that we cannot. I wouldn't use this type of method to compute the maximum daily to compute the upper bound of a maximum daily temperature. Okay, so you're talking about more moderate events. Yes, actually. I give weights to the choice of the analogs, and those weights can be tuned. So I tuned those weights to have to simulate events that have a very low probability, but I could use weights to simulate events that have a higher probability, of course.
Okay, thank you. Other questions? No. So we can move to the next speaker. It's Erika Coppola.
Yes, I'm here.
Pascal, could you stop sharing the screen, please?
I'll try. I don't know how. Okay, if I do this.
Okay, perfect. And Erika, now you can share.
Yes, I try now because I could not before. Okay.
Here the button.
Sorry, I think sharing the screen just restarted the system. I'll try again. It's something random happening. Can you see my screen now?
Yes.
Okay, that's good. Okay, so first of all, thanks for inviting me there, Valerio and Simona, and I'm really sorry that I could not be with you today for some reason that are independent from me. And I hope now that you will enjoy this different kind of extreme, because we will jump now on the convection extreme. And in the specific, I'll try to summarize what we have learned in this last, let's say, 5 to 10 years about the impact of climate change on convective extreme, using this convective resolving model that we start to use a few years ago, and what we think, how we think we will evolve in the future. So where we are at the moment. So most of the limited area model community has tried and is able to run high resolution simulation for climate projection, in which we reach resolution in which the convection parameterization can be switched off. and we can resolve explicitly the convection. These are just two examples from our model. One is the summer convection that is generated inside the domain over the Alpine and the Balkan. The other one is a fall example of frontal precipitation entering the system. You can see there is a very good agreement between the boundary, that is the era 5, and the inner domain, that is the gray one, in which we use the high resolution model with the explicit convection. So to start with, the question is, why did we start this effort? Because it was really a major effort. The answer is because we want to represent some scale process and interaction that are really crucial, have very high resolution scale to understand and to represent the local climate. We were hoping to be able to reduce the uncertainty when we go in projection mode for some specific statistic, like for example, the sub-daily statistic. And also we wanted to learn something new that are possible to study at such scale. And why we thought the multimodal approach was needed. First of all, because all of us know well the Kolmogorov work. So we wanted to build robustness of evidence about the previous study that have been using single model. We wanted to try to generalize some aspects that were already highlighted in some specific study in some specific area. And also we wanted to assess the ability of our model to do this exercise and to be able to represent the climate at such resolution. So we did this in a coordinated way, and we did this not only in Europe, but in many places over the world. So we did in Europe, in Africa, in South America, and in South Asia. And we all work, not in every project, but in a coordinated way in each of these regions. But today we will mostly focus on Europe, of course. So what we have learned in the year of study, and what our ensemble of model that is quite unique, because it was the first of this kind of ensemble that was created. So of course we were able to confirm what we already have seen from single model study in several regions of the world. So if we look, for example, at the mean hourly precipitation in the summer, so you see in the upper row, you have the observation. We look at 3 different statistics: the frequency, the intensity, and the heavy precipitation, the 99.9 percentile. And if you compare these statistics, so you see that there is a mask, because these are we show the statistic only over the region where we have the observation. That is, of course, a bottleneck for the model validation at such resolution. And if you compare this statistic with the 3-kilometer convection resolving model result with the 12-kilometer model in which we have the parameterized convection, you see clearly that there is advantage in using such resolution and explicitly reproducing the convection. But what about the spread of the model? Of course, as we expected, the model spread is large. There is a large variability. But still, if you compare all the ensemble members, these are all the members that we have of the ensemble, at high resolution compared with the observation and the lower resolution but parameterized convection, you see a clear difference between the 2 resolutions. But what instead, if we look at the projection mode, how are we able to, what is this variability telling us, and what is the uncertainty doing? So as we were hoping, it seems that at such resolution, the uncertainty is decreasing. Now, just to stay with me for a second, so on your left side, you have a present day 3 statistics, the same as before. So you have the heavy precipitation, the frequency, the intensity for different regions where we have the observation that are hourly, for the summer season, JJA, and for the fall. And on your right side, you have the future projection of the same statistic for the hourly precipitation. Without carefully look, but what you can see is that if you compare the red box with the blue box, in all region, in most of the indices and season, the size of the red box is smaller. So you have a smaller uncertainty when you go high resolution and you are able to represent the convection explicitly. But we wanted to investigate even more. So by using a bootstrap technique, we wanted to look at the fractional contribution of the model uncertainty to the total uncertainty. So what you see here represented is the PDF of the fractional contribution to the total precipitation, and you see that for the sorry that I don't see anymore the screen. Okay, you see that the model uncertainty contribution to the total uncertainty is in blue for the regional climate model with the parameterized convection, and is around 46%. While for the convection permitting model is in red and is about 30%. And it drops even at 25% for the extreme, while for the RCM remains stable. So the convergence in the explicit model high resolution is likely to be linked to the explicit representation of the convection. Indeed, if you compare this behavior in the winter season, where of course convection is less dominant, you see that the difference is much smaller. So somehow this was a kind of confirming what we have been seeing in the more simple statistical analysis. Then, thanks to this, the availability of the ensemble and the possibility to use tracking algorithm to investigate the evolution of the property of this system, we were able to study how the characteristic of the high precipitation events were changing, looking at the whole system. So how the evolution of this cell were changing, what was happening to the duration, for example, to the distance, the speed, and the volume. And in particular, if we look also at the yearly distribution of these high precipitation events, and we look at the difference between the historical, the blue arrow, and the far future, the red arrow, we see also a change in the modality of the distribution that is shifting from unimodal to bimodal, in which we have two peaks during the year in which these events are happening more frequently, that are in the months of June and October. And in general, what we can see is that there are some specific regions over the domain that we are studying that are like hotspot for this kind of heavy precipitation events that are highlighted in these figures. In the red, the greenish, the more green are these hotspots that we identify. And each of them, in average, we see that the duration of these events is longer. So this is the percentage change of this event. The distance travel is longer. The speed is faster. The volume is bigger of this cell. The mean and extreme precipitation is also increasing, and also the severity of these events. That is a combination of all these properties together. Then the other things that we wanted to ask ourselves is what are the characteristics now that we see this what is happening at the property of the precipitation at the surface, which are the large scale dynamic signature in the present, and what is the sensitivity of this to climate change in the future. So we focus our attention, starting from some case study, on some of these high precipitation events, the real one. I will illustrate just one in this study, but of course we are doing for all the category. So in this example, we are focusing on one extreme precipitation event that was very damaging, using a lot of damage all across North Europe. And in particular, in this example that I will show you later, I will focus on this region, in the northeastern region, where we are, where I am at the moment. And focusing on this, we developed a method to identify which are the events similar to those one that has been so catastrophic in time. So this is the red events, the red arrow represent these specific events. And we were looking in the present day time series, which were the similar events that were happening in the same region. We used two different methods, one looking at the percentage of area in which we observe a very high percentile of precipitation happening, and the other one based on the storm track algorithm that I showed you before. So by using these two methods, basically we were looking at what is how these events are represented by our model. In the specificity of this, we had only 4 models that we were using, and we were looking how the number of these similar and analog events were changing, going from the present day to the future, so the yellow and the red in 4 of this model. And then we ask ourselves, what is based on this ensemble approach, which are the large scale characteristics that we want to use to identify the peculiarity of these events in this region of Italy in the specificity of the example. So we look at the mean large scale dynamical signature, and we were using the mean sea level pressure and the 500 geopotential high. We look at all these events in the era 5, the driving of the high resolution simulation, and the mean signature for the mean sea level pressure and the geopotential height look like that. So then we look at the same signature in the ensemble of the evaluation simulation, so driven by the era 5. And then we look at the same things in the scenario simulation, so the simulation driven by a GCM. And then, of course, once we identify the events by using this large scale variable, we are interested in looking at what is the change in the future. So here you see represented the same quantity for the historical period, the end of century, and the change. What we can see is that there is a difference in the mechanism that is driving these events. The large scale pattern of these events show a shallower unstable flow in the future, but with blocking configuration that are favored over the Eastern Mediterranean and are confining the perturbation over the Western. Of course, this is associated with an increase of temperature, and if we look at the change in the water vapor variable, so the integrated water vapor over the column and the difference between the historical and the future, we see that there is an increase of course, of water vapor in the future condition. But surprisingly, this is instead the change of the 850 millibar wind. We have a decrease of the close to surface wind at this corresponding to this pattern. So there is a larger variability of water vapor across the flow, feeding the northeast of the Alps, and there is a slowdown of this wind at the surface, that also is favoring water vapor load of the upstream flow in this region. So what we have learned is that for the impact of climate change or the global warming is pushing these kind of events to increase in frequency, and the heat area that these events are affecting is also increasing. And the large-scale pattern of these kind of events are changing in the future with the change that I highlighted before. What we also have seen that is not reported here is that in the case in which this kind of high precipitation event is mainly driven by the a well-set forcing, like for example orographic or cold front, the model are very well able to represent them and then agree also in the future path. When we have something that is driven by a more complex interaction like prefrontal or MCS formation, there is a larger, of course, variability among the models. But then the next question also that we ask ourselves is, can we use this model to look at compound extreme precipitation events and attribute these to the global warming? So the question we are trying to answer, and this is really work in progress, is global warming increasing both the frequency and the extent of this impact across multiple regions simultaneously? So are we observing really an increase in the area of that is hit by this kind of events, and also simultaneously means in many regions in the same, many small regions in the same big region? So we did some study, and this is just briefly shown here. So here there are several sub-regions in Italy, specifically called as the name of the region that we have in Italy. And this is the time evolution. So what we see using different kind of observation is that this you have the increase of fractional area that is hit by this kind of events, and also the number of regions that are hit is increasing. And this trend that is significant for each of these regions we have considered is also reproduced by the model and projected to the future. All these trends that are shown are significantly different. We are also completing the dynamical study of associated to this. So just to go to the conclusion, then what we have been able to learn in this less than 10 years. Of course, we have been able to improve consolidate the result that we had earlier. So we have for sure better statistic of the frequency intensity of the precipitation events. We can improve the diurnal cycle of the precipitation and the representation of the very extreme tail of the distribution. So I've been consolidating what we expected to kind of learn before. We've been able to reduce the uncertainty for the present day climate. And also, it seems that this is kept for the future projection. We had the possibility to study the change of the property of these high precipitation events and understand how they evolve due to the warming of the atmosphere. But now the question is, we want to move forward and we want to ask ourselves, can we trust this result? And what we need to even more have to add more robustness to what we have learned, and what we should concentrate to work on. And what we think as a community is that it's important to keep this coordinated effort, because we have learned a lot thanks to that. We need to keep this ensemble populated because we want to ensure the robustness of the result. Many of these results could be not possible without such an ensemble. we need to leave the room for complementary approach, like for example, the machine learning. And we are already moving towards this direction. This is again another preliminary result. So we ask ourselves, can we use an emulator to emulate those models that are very costly in terms of computer resource? So this is the same events that we have looked before with the 3 regions where we had the flooding. This is the dynamical model ensemble. So how the ensemble of the model we have seen before is reproducing the events. This is the mean and this is the median of the ensemble. And this is how the machine learning algorithm can reproduce the same events trained on the real world, means trained with the error file, or trained with the model, means the same driving of the dynamical model. So as a last, of course, we also need to work on a lot on model development, but again together, because reaching such a resolution needs and require an update of all the physical parameterization that were not meant for such resolution. So first of all, we need to have the urban parameterization. We need to keep using the vegetation dynamically. Some of the models are already doing. The hydrology and the groundwater, it's important at such resolution. There are several studies have shown already that. So this interaction is key and crucial to be included. The aerosol, of course, both prescribing and evolving, the sea ice, the glacier, the land and water use scenario that are not implemented at the moment. And of course, the ocean, so the coupled system that are partially implemented in several regions, and the human component. And with this, I thank you for listening.
Thank you, Erika, to be perfectly on time. And any question? Yeah.
We are about one step back.
Yes.
Hey, Erika, thank you so much for the great talk. I had a couple of questions. They're kind of different. One is just about the last point, where you talked about using machine learning.
Can I ask you to come closer to the microphone, because I hear a kind of like very.
Can you hear me now?
Yes, now it's better.
Oh,
on the line.
Yeah, and I can see you.
Sorry, it was dark in the window.
So I was just saying, thank you for the great talk. I was just going to ask you 2 questions. One is about the like emulation of precipitation. Did you only emulate the like parts of the parameterization, or was it the whole flow?
Okay, so the emulator works with the predictor that we use for the emulator are the large scale quantity that typically you have in the model. So you have the vertical profile at several grid points, and you try to emulate the model, the dynamical model itself. So given this predictor, so the large scale predictor, and of course the surface information in the specificity, the topography, you ask the emulator to reproduce the precipitation.
I see.
So you don't emulate the parameterization in the model, but you try to emulate the model itself.
Mm-hmm. So it's like a kind of downscaling type approach.
Yes.
Yeah. Okay. And then the other question was about the bimodal seasonal cycle that kind of emerged in one of the plots. I was just curious. So presumably this is somehow controlled by the large scale circulation. Is this something that wasn't as apparent in the lower resolution case? Maybe I missed it.
Exactly. Yeah, no, I didn't show the result that you missed. So no, it's only appearing when you are able to really track the system. So if you study simply using a parameterized model, the ensemble of, for example, the 12-kilometer ensemble, and you look at the distribution of extreme precipitation events, but using any metrics like any percentile, extreme percentile, it doesn't really show any change of the distribution. the specificity of this is that we don't use any percentile because now we are able to track the system. And then when we look at the distribution of the frequency of the tracked system, then the bimodal distribution appears.
I see. Okay, thank you.
You're welcome.
The question?
Thanks, Eric. I also have two short questions. The first one is about the extreme event that you showed, the one over Friuli, and I was very impressed by the increasing precipitation of water that we see in the future climate. So maybe you said and I've missed, but how is the SSTs, how are the SSTs in the Mediterranean treated here in the simulation?
How is in, you mean what is the change of the SST? Or
yes,
what
like,
are the SST?
I guess they are increasing the SSTs, but how are they in the model?
They are taken from the driving model that in this specific, this model, this high resolution model are nested on the 12-kilometer lower resolution model, and they are nested on the GCM. So basically the SST is derived from the GCM and interpolated on the resolution that that we have first at 12 and then at 3 kilometer. So the SST are taken from the driving GCM.
Yeah, so they evolve. So now it's a couple.
Yeah, of course. Yeah.
Right. And the second question is, this is an event that you said is driven by a large scale. There is a clear large scale forcing, and you also said that on the other hand, the very prefrontal small scale events are difficult to predict or to analyze in this way. I was wondering if you have tried to analyze some of these events, or if you can share a bit more about what you see are the main challenges and difficulties.
Okay, so the main challenge and difficulty is to to apply this finding method for this kind of events, because not all the model, because you have to be able, I didn't really specify this well, but first you have to be able to make sure that those events are correct, right? So you have to look at analog of these events, that is this disastrous one, and then you have to make sure that these green events, the one that you see here in the reality, are really they are events that have happened in the reality. So they were as well very high precipitation events, for example, recorded in the news or that reported somewhere, and they are. So in the case in which we look at similar events that are not so well, so like mesoscale or this kind of events that are not, is a multiple interaction, so like topography, but also kind of trough entering, then in that case, the identification of the analog is not as easy as in this case. And so all the chain is more difficult, because then you don't want to mix up orange and apple, right? You want to make sure that what you are selecting, both in the real world and in the model world, it's a similar kind of large scale condition that are interacting with the local scale, in this case topography, and then producing this kind of system.
Yeah, thank you very much.
You're welcome.
Thank you, Erica. Valerio?
Just a silly technical question. I'm always confused. I'm always confused when you talk about convective permitting, which is not convective resolving, right? So
well, the terminology is very disputable. I mean, there are some of the people that don't like convection permitting, and convection resolving can be messed up with the real cloud resolving model, and this is something that it's not what we have. I mean, we have dynamical models that are not using the parameterize of the convection. So, I mean, this is what we mean. So we are using model and a resolution in which the parameterization of the convection is off. So basically, everything that is connected with convection is represented by the model itself.
Okay, thank you.
Yeah.
Thank you, Erika. So it's time
Welcome.
for the coffee break, but we are really late, so I think that we can just take 15 minutes of a coffee break and then reconvene at 5 p.m. more or less. See you later.
che interno no, dico che interno però nascondi nascondi ora sì, ci dico io, puoi metterlo a schermo interno. Perfetto.
Okay, so we can resume with the last three talks. Now is the turn of Ronan McCallum. So
You want to stay here?
I'll stay here, yeah.
Okay.
Seemed to work last time. So.
Yeah, it worked.
Good, okay.
Okay.
Okay then, well I hope everyone online and at the back can hear me.
No, louder.
No, louder, okay.
Sharp
I
and
will do my
sweet.
best to maintain this volume, okay. Great, first of all, thanks very much for the opportunity to be here for the organisers. I'm an oceanographer by training, so this workshop has been quite educational and very, very well done. So thank you all for educating me in many aspects. I'm going to bring something a little bit new to the table, something I haven't yet seen so much so far, a little bit of machine learning. So I'm going to be talking about the feature selection framework, which is a method we're developing to detect drivers of various heat extremes, which could be heat waves, but we also look at warm nights as well. Now, I should say that a lot of this work has been performed by a PhD student at the University of Alcalá, Cesar Palias Rodriguez, brilliant PhD student that we're collaborating with, also collaborating with Bologna in Italy. So the title is very long, so I'll need a whole talk to explain it, so let me jump straight in. First of all, let's have a look at the background, what is being done in data-driven methods, specifically for heat extremes. And then I will talk about why I think our method is particularly novel, particularly different to other ones, and show a few, let's say, preliminary results, a proof of concept for a case study of the north of Italy in Lake Como. So what do we know? It's possible with statistical seasonal forecasts to predict fairly well summer temperatures using very few predictors. North Atlantic SFT, Z500, area average variables. And what I mean by fairly well is actually some dynamical systems can be matched or even outperformed by these simple statistical forecasts. And similar experiences are being found with machine learning and deep learning methods, again, using very few variables, training on those and managing to recreate either extreme temperatures or heat waves themselves. Beyond that, other studies are looking at explaining machine learning. Of course, explainability is a big issue these days, and studies are doing that by, for example, ranking variables in order of contribution to forecast skill, looking at light correlations, looking at ways of clustering the target variables and the predictor variables. Our aim is very much similar to those studies. Many people are doing it. But with our methodology, which you will see, we want to give the machine learning, a chance to choose what the drivers are, rather than us kind of holding its hand and telling us what the predictor should be. So let me explain that in a few moments. First of all, our target data, as I said, we're starting with a case study in Lake Como for various reasons to do with agriculture and water supply. On the right there is just a two-dimensional time series of the heatwave data we're looking at. So of course, there's many more in a more recent period. Black is showing where there is a heatwave, white where there isn't. And the main point from this visualization is that, of course, we're dealing with a very imbalanced data set. There's many more non-extreme days and extreme days, naturally. And that itself is a problem for any kind of machine learning-based work. So that was the target data. This is the predictor data. What we're doing is we're taking ERA 5 atmospheric variables, as you can see them on the left, and we're simply applying a k-mean spatial clustering of that long period, 1951 to 2010. And what you get is, well, depending on whether you do it globally or in the Arctic or over Europe, you get these quite large areas representing the main modes of variability in these areas. So we're actually reducing the dimensionality quite a lot. You can see these very large regions of which we take the area average. So we're taking area average mean sea level pressure over the whole Mediterranean of the European region. So quite a lot of dimensionality being reduced there. So we take the target, we take the predictor data, and I won't explain this very well because I didn't develop it. The good colleagues at University of Alcalá did. But what we're doing is running something called an optimization algorithm. It's called a coral reef optimization because the metaphor here is quite strong. Imagine a coral reef with various species of larvae all competing for growing space, evolution space on a very small outcrop or rock. And so they're all competing and trying to beat each other to evolve. Instead of larvae here, we are inputting our various clusters, a time lag, so from 0 to 180 days, and a sequence length. So on what time that cluster would be important. Is it important for 10 days, 20 days? So all these solutions are competing for, well, let's say solution space. And they're doing that by running a logistic regression model trained on these combinations of solutions, and they're being optimized based on an F1 score. I will show some results to hopefully give you a better idea of what that all means. So this is what the optimization algorithm run looks like. First of all, we don't just run the optimization algorithm once because there is some inherent randomness to it. So we run it 10 independent times, each time letting it go for 15,000 evaluations. So we essentially have 150,000 solutions. And what we're seeing here in the black is simply the validation period score. So that's validated on the training periods, which is all the data before 2010. And in blue, we have the test period, which is the data after the training period. So as we expect, the test period is not predicted as well as the training period. There is some level of overfitting, as expected. But each, as I say, each point here is a solution. You can see that some of the best solutions have a validation score of 0.55 and an equivalent test score of 0.36. We can debate about whether that's good, but considering we're really reducing the dimensionality quite a lot, to be able to recreate the last 10 years of heat wave daily data with an F1 score of 0.54 is already quite encouraging, I think. But let's explore that in a bit more detail. As I say, each of these points is a solution, so each of those solutions has decided that certain clusters are important and certain time lags are important. And this, in this experiment anyway, preliminary experiment, this is what it has found. We're going to measure importance by the discard rate. So each of those points you saw on the previous slide has decided to either keep or discard clusters. And what we're finding is that if we look at the top, what's that, 10 or 15, we see the clusters that have been discarded the least. So the most important cluster, which is never discarded, is 2-meter temperature cluster 2 in Europe, which is, unsurprisingly, the 2-meter temperature over Lake Como itself. And then other ones you see, like the Z500 over Europe, the soil moisture, they are again local clusters. So far, it's not, the optimization algorithm has decided that these local variables are key in predicting heat waves. So far, it's not a surprising result, but in a way, it's a validation that it has the, well, intelligence to detect that. Interestingly, it's also in second place detected the outgoing long-wave radiation, cluster 3 from the global clustering, which is this brown one in the Western Pacific. Now, we haven't checked that explicitly, I must say, but we have a feeling it's some sort of indicator of ENSO, but to be confirmed. So, not only can we choose the clusters, as I said, we can also choose the time lags. And this is very hard to see even on this big screen, but basically what we have for each variable in each cluster, 1, 2, 3, 4, 5, we have the days to the target day in which it was important. So the main example is that 2-meter cluster over Lake Como is naturally important within the timescales of a week to 2 weeks, maybe going up to 3. Likewise, the atmospheric circulation represented by Z500 cluster is again working on a very short time scale, up to 2 weeks. The OLR cluster, which I pointed out in the West Pacific, actually is active on more of a sub-seasonal timescale. So this method seems to be detecting quite strong sub-seasonal drivers as well, which is quite encouraging. There are other signals, but you can see they're much weaker. And actually, if you rerun this again, they sometimes drop out as noise. So we're really going to focus on some of these stronger signals. And as I've said so far, perhaps the physical interpretation of this isn't very surprising so far. But if we take these 3 variables, the atmospheric circulation, the cumulative temperature of Europe, and this supposed teleconnection to the Western Pacific, if we say, well, they seem to be chosen all the time, what if we take them out? Do we have enough skill? So we do that, and we ask ourselves, well, what happens if they are removed? And here is what I showed you before, the solution space for the original experiment. And here is what happens when you remove these so-called VIP variables. And actually, not very much has happened. Okay? So the cross-validation scores, the test skills, are still quite similar. And what we find is that the discard rate shows us that the variables that were previously in 3rd place, 4th place, 5th place, have all been pushed up. And it seems in terms of the skill scores that you can reach, they're quite capable of doing the job that the cumulative temperature of the atmospheric circulation did. So precipitation here over Europe is considered an absolutely necessary driver for heat waves. Soil moisture too in various clusters in Europe. And again, we're in some of these cases, we're still talking about short-term drivers, sort of precipitation and the soil moisture. But if even I'm struggling to see here, apologies, but if you look at the mean sea level Europe cluster 3, which corresponds to this brown cluster over the subpolar and North Atlantic, I think, yes, that corresponds to, again, to sub-seasonal, even onwards to seasonal timescales. Again, something to check, but it seems to imply there's some sort of link to the NAO, which is quite encouraging that the algorithms detected that. So, I said that the skills are quite similar. What we can do is, the skills I've shown you so far have been with a simple logistic regression model. Now we introduce it with machine learning. We can take those same solutions and train a bit more sophisticated model on those solutions. So that's why we take 2 minutes, okay. We take, for example, gradient boost, random forest, etc. And we find that we can actually achieve F1 scores of up to 0.6 with the same solutions. It's even more encouraging. And this is a comparison between the VIP variables and the all included variables. And we find that on average here, if you take out those so-called VIP variables, there is a slight decrease, but actually you're still, in some cases, quite capable of making the same quality predictions, level of quality, level of skill. So, lastly, we are applying this not just to heat waves, but to other kind of indices. We've taken, for example, simply the 90th percentile, the days which exceed the 90th percentile, which should be a slightly easier target. And indeed, we see the test scores, they do slightly increase. We did an experiment where we removed any information from 20 days prior to the heat wave. So I've called that a sub-seasonal to seasonal experiment, if you're only taking the longer-term information, and the skill halves, so that we can begin to quantify the contribution of various time lags to skill. And for warm nights, it's a bit more of an imbalanced data set, actually. There's fewer on record, so the skill is indeed going down. Very finally, what's this got to do with Rossby waves? Well, at the moment, we have quite a crude representation of the driver variables, these very large clusters. We can do something a bit more intelligent, maybe. We can take an NAO index instead of an area average per cluster, or we can start looking at indices for propagating wave patterns. I found this CEOF used in Majunga et al. 2019, and perhaps there's many of the indices that yourselves are using. We can somehow find a way and get them to compete in this optimization algorithm. So those are the conclusions. I will finish by saying, please come to the poster by my colleague Antonello, so we can discuss this method more. Thanks very much.
Are there any questions for Ronan? Yes.
Yeah, hi. Thanks for the interesting talk. I was wondering about the k-means clustering a bit, because did I understand correctly that you cluster either on Europe or globally for every variable by itself?
Yeah, there is some repetition. For example, for SST, we do a North Atlantic clustering, then we do a global clustering.
Okay, because what I'm wondering about, first, you have to choose the number of clusters.
Yes.
Second, by choosing whether you cluster in which region and on what variables you might influence. And then if there are physical processes that connect different variables, by clustering both variables, you might focus on that process, right?
Yes. Yes.
So why did you choose the way you choose?
Good point. There's a lot of arbitrary decisions there so far. We're playing with different numbers of clusters in the hope of seeing the general F1 score go up, maybe to capture a bit more precise predictor data. As I mentioned at the start, we're kind of trying to find a way, instead of giving machine learning algorithms kind of our interpretation of what's important, we want to let it choose, let the various clusters fight. But of course, we need to define something to give it. And that's probably why we see that if you take out 2 meter temperature, precipitation takes over, so a monster takes over. It's similar, exactly. So there's similar signals in both variables.
Okay.
It's a good question. We're still thinking about.
Yeah.
So
Thank you.
Yes. Maybe
maybe
just because I really had the same question on the regionalization, and my work has had kind of the same kind of problem, and I came across this machine. So if you were into machine learning, this architecture called a visual transformer or image transformer, whatever they want to call it, where you can really see the neural network focusing on some parts of some image more, or I mean, they use it to make detection or classification. But for this problem, it seems like it would be a good choice, because then you would make even fewer assumptions. You would let the model decide which regions are important for this and that. Have you thought of that?
Am I mistaken in thinking that's more of a deep learning method?
Yeah.
Okay. At the moment, I think the optimization algorithm itself is not machine learning, but the way we train the forecast, we use various machine learning algorithms. We haven't got to the level of complexity yet.
And isn't there somewhere in between where you would just grid, like with just a coarser resolution, and then just let it go, whatever? But yeah, there's maybe something in between.
I guess the question is how far do you reduce the dimensionality?
Yeah.
Ideally, you'd have, instead of clusters, you'd have every grid point of Europe or the world, but that would be an enormous task. Yeah. Possibly.
Other question? No. Okay. Thank you, Ron.
Thank you.
Thank you. And the next speaker is Frank Kwasniak. I'm sorry for the bad pronunciation.
Yeah, it's fine. Can you hear me? Can you hear me?
Yeah, we can hear you.
I try to share my screen.
Okay.
Yes.
Okay, we can see your. Yes.
Can I use my screen in large format? Is large enough?
It's not full screen.
Not full screen. Oh, how can I do it? But is it large enough, or is it okay?
It is large enough, but if you can make it full screen, maybe it's even better. Otherwise, no worries.
Oh, yeah, how to do it full screen? I don't know.
Is it a PDF?
Now it's better?
Yeah, now it's better. Much better. Yeah.
Okay. And can you see the slides moving?
Yes.
Yes.
That's fine. Okay, then I start. So my present talk is on quantifying weather and climate risk using data-driven large deviation theory. My talk has two parts. First of all, I will briefly introduce large deviation theory, and particularly data-driven large deviation theory, what you can derive from pure observations. Then second part is applications of the methodology to a couple of systems, ranging from a toy model to more realistic meteorological situations. So a brief motivation. Large deviation theory is about quantifying the likelihood of persistent extremes, or of rare trajectories in the language of dynamical systems. So very simple example, the well-known Lorentz 63 system. This is double wing attractor. You can see at the bottom two panels, two trajectories of the system. The left one is a fairly typical trajectory where we have equal proportion of the regimes. So probability x is positive. For example, it's the x variable. So x is positive is around 1/2 because the system is completely symmetric. So in the long term, we expect half of the time in the upper part and in the lower part. The right panel shows a highly unlikely trajectory from the same system. It's a frame of 100 system units, and the system spends about 77% of the time on the upper wing for x positive. So that's a highly unlikely long-term trajectory. Now, large deviation theory is about quantifying the likelihood. So if you pick a frame, say, of 100 time units from a long integration, what's the probability of observing such an extreme, such a persistent extreme? And this obviously relates to heat waves and cold snaps in terms of meteorology and climate. And we do this on the basis, just on the basis of data. So it's purely data-driven, what I'm doing here. So a brief overview on large deviation theory. Just in a nutshell, the main cornerstone, if you do it from data, is the so-called Gärtner-Ellis theorem. So large deviation theory is about statements about sample means. So we have a set of variables xi, which are identically distributed random variables, not necessarily independent. So there may be serial correlation. They may stem, for example, from a dynamical system, from a long-term integration. And then you almost always have serial correlation. Then we look at the random variable an, which is the sample mean of n consecutive observations. Now the main statement is, we need to consider this gamma function. That's the so-called scaled cumulant generating function. This gamma function, the scalar function, is defined as this limit here, limit n to infinity, 1 over n, and then log of expectation of this exponential function. And if this exists, so if it's finite and exists, and it is differential everywhere, then the probability distribution of an follows a so-called large deviation principle. That means there is a probability density that an is equal to z is proportional to exponential minus ni of z. And this I of z function is a so-called large deviation rate function. And it's universal once n is large enough. So once n is large enough, you have convergence, and then the I of z is independent of n. That means the shape of the distribution is the same. Of the PDF just scales linearly with n once convergence is achieved. And this large deviation rate function I of z can be obtained as a Legendre transform of the scaled cumulant generation function. So that's the recipe. Then if we know this rate function, we can deduce the probability density of even larger sample means. So it's a kind of extrapolation with respect to n. So for example, we have observations of temperature averages over 7 days, 14 days. Then we can calculate this rate function, estimate the rate function. Once we have convergence, we can then extrapolate to longer periods. So for example, to monthly means 30 days, or a whole summer season, 90 days. Then we can have better use of the observations. So we just need 7-day or 14-day means and can still deduce longer periods. So that's the main aim here, what we are doing. It's all just from data, so just a time series of xi is given. Properties of the rate function. The rate function is strictly convex everywhere, so the curvature is positive. The rate function has a unique zero and minimum at the mean of x. And there is a connection with the central limit theorem. For small deviations around the mean, the curvature of the rate function at the mean is just the inverse of the scaled variance. That's the central limit theorem. So that's for small deviations. That's a Gaussian approximation, if you like. And then the large deviation theory is the next order, deals with larger deviations. In the limit, we will cover the central limit theorem as we expect. Now to estimate the rate function purely from data, there are basically two methods. First is the Legendre transform method. We just take the definition of this I as a Legendre transform of the cumulant generating function. And then we just replace the expectation with the sample mean. Just canonical procedure in statistics. And then we get a sample estimate of this rate function. Then we would do this for increasing n and compare this. And once we have convergence, we have calculated the rate function. Alternatively, we can use the probability density. So we look at the sample means, and then we just calculate the probability density. And from the structure of the problem, it's natural to deal with exponential families. So to make an ansatz for the probability density as exponential, some potential function minus u. And then we make an ansatz for this u function in terms of, for example, polynomial or spline basis functions. These phi I are basis functions, pre-chosen basis functions. Polynomials or splines is natural choice. Then we have the u, and then we know the rate function is then proportional to u. It's just in the limit 1 over n times u. And then if n is large enough, we would hope for convergence. And then we have also control of the convergence, and we know we have the probability directly estimated. So it gives us a clue if convergence is reached or not. So what actually probability density is. And then you can come up with a third method, if you like, where you constrain this probability density fit with these properties of the rate function, which we had in the previous slide. We have these constraints. There must be a 0 at the mean value, must be a minimum, and we can incorporate these. And we can also incorporate this curvature at the minimum from the central limit theorem. So we can calculate the scaled variance. Then we can impose to the maximum likelihood fit of the probability density these constraints. That's a bit a third method, if you like. We would hope for a better rate function because we implant these properties for the rate function we know must hold. Then we do the constraint maximum likelihood estimation of this exponential family model. So that's the procedure. We have continuous systems, and we have, say, a sampling rate delta t, and then n consecutive values extend over a time period of tau. Then tau is n delta t. Okay, a very simple example with IID variables, so just independent variables from exponential distribution with parameter 1. Then we can calculate this analytically from the Legendre transform. So the rate function is known as this linear part z minus I, and then the logarithmic part close to 0. Near the two panels with 500 data points and 5,000 data points, an estimate of the PDF. The blue is the truth, and the red is the estimate with uncertainty. So we see where most of the data are is very accurate, already with 500 data points. And then further out in the extreme range, the error is a bit larger, as we expect, because there are few data points. Then with 5,000 points, it gets better, considerably better. That's a simple example without serial correlation. And now applications. We go back to this Lorentz S63 system with this regime occurrence, the regime proportion. We apply this to the setting. And this is a rate function we get for the proportion of the regime. So the probability that x is positive, so we're in the upper wing of the attractor. And that's the rate function estimates. Tau is a period increasing. Tau is 10, 15, 20, 25. These are the estimates from the PDF and from the Legendre transform. So we observe pretty fast convergence here. Basically after 10, so tau equal 10 is already quite converged. So most of the rate function is already converged after 10 system units. And the information is slightly different from the PDF and Legendre transform. Then the right panel is the return level. So like in extreme value theory, from this probability density or probability distribution, you can calculate return levels. So as a function of the return period. So how many with the number of windows of a certain length you have to pick to get a certain return level. These
2 minutes.
Yeah, okay. Oh, it's 2 minutes? No, it's a bit, must be 5 minutes, 15 minutes in total. I started 28 only. It's just 10 minutes gone now. I think it's 5 minutes left. That's a return level. So let's say the curve we get. And here we have enough data. We can have millions of data, so we can check this. And the green is the truth, actually. And it's quite good. So it's in between the PDF and the Laurent transform. Okay, then a more realistic example, wind speed in an atmospheric model. It's a 3-level QG model, standard QG model. It's similar to the Marshall and Mortani model. We just look at wind speed at a certain grid point in the North Atlantic area. Take a long time here, since 10,000 of days of data. Then this is a PDF, so it's a bit gamma-like. And these are trajectories. Left is a typical trajectory, then a very high wind speed on average, and a very low wind speed. And that's 100 days, so it's seasonal time scale. So it would be a particularly stormy season or particularly calm season related to regimes in the atmospheric circulation, the underlying regime. So it's unusual persistence of blocking or solar regime. So it creates then the storminess or lack of storminess. And this is a rate function for this example. So we have convergence, say after, well, 15 or 20 days, we have some convergence. Then again, the return level. Here is the agree PDF and Laurent transform. And still we can create millions of data points here. So the green is a check, it's a truth for many, many data. And it's quite good. So it's quite verifies this estimate from the shorter data set from the large deviation theory. Now let's look at UK heat waves. That's the Central England temperature time series. So that's a spatial average over Central England, a couple of stations, average spatially. And then it's a daily mean temperature for 60 years here from 1960 to recent past. Then we apply the algorithm. This is a PDF. So the red is the total period, and then blue and green are the halves, the first half and the second half. So we can see climate change. So there's a shift, so the summer temperatures have become warmer. And we pick just the summer temperatures, June, July, August. And then again, trajectories. And these are extreme trajectories from this famous heat wave 76 over the UK, which is still unbeaten on persistence. And there's a chunk 14 days, 30 days, and the whole summer 92 days. And this is really a high, very high average. So here 22 is already, as for this single data point, is already the tail of the distribution. This is a mean over 14 days. This is an extreme heat wave. It was an extreme season in total. Now large deviation theory applied to this, that's a rate function. So here convergence is a bit slower. We need 25 or 30 days averaging to achieve convergence. And that's a return level. We get for 30 days for a monthly mean and 92, so for the whole summer season. That's a dotted line or dashed line. That's a return level we get. And the horizontal black lines are these famous heat wave 76. So for the whole summer would be 1 in 100 years about. And for this 30-day period, it's even more extreme. So you would have to pick thousands of such windows to get this. So it's overall it's realistic return levels. Actually, for cold summer temperatures, the convergence is faster, as you can see on the left side of this large deviation function. That's related to the regime. So it's shorter lived. The westerly wind regimes have a shorter time scale, and these heat waves are associated with blocking with a longer time scale. So we expect convergence to be slower for the heat waves and faster for the cold summers. That's what we will cover here. Now, last slide, the shift in the rate function. So if we do it separately for the first half and the second half of the data set, we get the blue rate function and the green rate function. Both with 30 days, tau with 30 days. So we see clearly the shift. Cool summers have become very less likely. It's quite a huge difference. So its likelihood is much lower now for particularly cool summers. And then hot summers, heat waves have become more probable. And that's a return level, blue and green. So the moderate extremes have become more often now in the second period of this time, so 90s to up to now. So there's an increased risk of heat waves, strongly increased. And the horizontal lines in black are again the 76 value. So we see in the first half of the data set would have been 1 in 200 years about this summer. And now for the second half, it's less rare. It's about 1 in 50 years or so, the risk. And also there's a 30-day average. For the very, very extremes, it's a bit a bias because there is this extreme data point as the 76 heat wave, which is still unbeaten. That means for the very extreme events, even the first period is more extreme. But I think that's just a data issue because we haven't yet sampled such an extreme data point in the second half. So it's just lack of data. If you put uncertainty, and we see the uncertainty is obviously large, very large for the very large extremes. Very extreme cases, there's a huge uncertainty. So it's within the uncertainty. Okay, brief conclusions. So data-driven large deviation theory allows to estimate the likelihood of persistent extremes or rare trajectories in the language of dynamical systems. So it could be heat waves, cold snaps, also precipitation or so accumulated over certain days or so, a number of heat days or so like this. So it's quite flexible, quite general. It's based on an extrapolation in the averaging period. So we hope we have the averages for 7 or 14 days, and then we can infer something about longer periods, which has not been observed. So the concept is a bit similar to an extreme value analysis. So we extrapolate beyond the observed data points. We have mapped changing weather and climate risk with time-dependent rate functions. If you work in sliding windows, you could map the evolution of the rate function over time. The analysis is complementary to classical GAV and GPD analysis because it deals with persistent extremes, which cannot be captured by the classical analysis. There are challenges with serial correlation, amount of data, and model specification. So for this rate function, we have to choose a model, and then there's a model selection, for example, with an information criterion. There's a bit of freedom. If you choose polynomials, how many spline functions, how many. And you have these different information, a bit slightly different from Legendre transform and PDF. So this has to be investigated further a bit to maybe on known examples to really work out which one is better in which situation. Okay, I stop here. Thanks for your attention.
Thank you, Frank. Yes, one quick question.
Yes, hi. Really interesting. So I was wondering, what would you recommend? Like, which way of estimating the rate function is better in terms of obtaining better return period estimates, the probability-based estimation, or the Legendre transform method? And then, so we did, I don't know if you are aware, but we did with Valerio we studied a similar topic, and so we also find the convergence of rate functions in case of heat waves for 30 days averages. But in your case, like the data length is much shorter than in our case. So I was wondering what part of your methods gives you this advantage of being able to estimate these rare events with relatively short time series.
So the first question, I think there is not yet a clear answer. Legendre transform versus PDF, which one is better? At first sight, Legendre transform is smoother and incorporates all these properties. So it's strictly convex, it has the correct minimum at the mean state and the correct curvature. So it has all the properties built in automatically. It's guaranteed for the Legendre transform. So that's a big advantage. On the other hand, you lose a bit control when convergence is reached, because even when convergence is not reached, you still have these properties. Then you cannot be sure. The PDF approach gives you a hand to directly check if you are converged. On the other hand, it's more wiggly, this PDF approach. As I briefly mentioned, there's a third approach where you constrain the PDF fit with these properties. And I think that's quite promising. I have to work this out more clearly to compare really these two, PDF without constraint and with constraints. I think it's very promising, this PDF fit maximum likelihood exponential family with constraints. I think it's quite promising. But I have to work this out. I have to choose a system where we know everything. So there are stochastic processes, very simple ones, where there's serial correlation, but you still know everything. You can work out everything analytically. Then you can really check many data points exactly versus the correct rate function, which one is better. which approach is better. I will check this. It's really a system where I can recheck this. Then the second question, I'm not completely sure how you calculated the rate function. I have the impression my ansatz is a bit more constrained for this potential function. I'm using polynomials or splines, just a few of them, and the maximum likelihood fit. This is obviously less wiggly than just a kernel estimator. So I think a kernel density estimator is very wiggly. And I think the maximum likelihood is clearly better because this problem has naturally the structure of an exponential family from the large deviation principle. It's exponential of this minus ni. So I think it's natural, canonical to use this exponential family approach and then maximum likelihood. Then with few basis functions. I think that's the reason, because I constrain it to fewer basis functions. Then you see a clearer convergence with fewer data points. I think that's the reason.
Okay. No, very interesting. Thank you.
Thank you. So I think it's time for the last talk of the day. Quan Liu.
Yes.
Can you please share your screen? Perfect.
Okay.
Go on.
So the title of my presentation is warmer is different. Internally generated summer North Atlantic oscillation extremes in a warming climate. Currently, I am a PhD in Max Planck Institute for Meteorology. I would start with the surface temperature this July. So here in Hamburg, the temperature could be as low as 5 degrees in the morning. It rained almost every day. But I guess in Bologna, it's heat wave, and the other regions in Mediterranean like Greece, they are preconditional wildfires. So this is a typical temperature pattern for negative NAO. But if we look at the monthly index of summer North Atlantic oscillation in the past 150 years, this year actually is not the worst case. There are years when the NAO index is above 1.5 standard deviation or below minus 1.5 standard deviation. Definitely those extremes would lead to severe surface weather conditions. Then one would be concerned will global warming increase the occurrence of such extreme cases? Before we get into that, let's have a look at the NAO time series. So it shows over various annual to multi-decadal variabilities, and the extremes could arise from or generated by those variabilities, which are actually the internal variability of the NAO. So it's fair to say that the summer NAO extremes are generated largely from internal variability. But global warming and internal variability have long been assumed as two independent concepts. Global warming represents the externally forced signal and always shown as a long-term trend, while the internal variability is an intrinsic property and is always assumed as stochastic noise. The atmospheric circulation undergoes both changes due to global warming and internal variability. Recently, their studies suggest that the internal variability of the NAO is not completely independent of global warming, which they referred as indirect NAO response. However, such indirect NAO response has not yet been examined in a transient simulation. Of particular concern is whether the extreme summer North Atlantic oscillation that are generated by internal variability is independent of global warming. To examine this question, we have to quantify the internal variability. Here we use a single model initial condition large ensemble simulations, or SMILES, In SMILES, the mean over ensemble dimension represents the direct response, which we mentioned before, while the deviation from the ensemble mean quantify the internal variability. Since we are interested in the internal variability only, this ensemble mean is removed from each of the ensemble members, but still we assume that the internal variability of NAO is time independent. So we decompose the NAO from the demeaned series independently every 10 years. So if the significant change occur between the last 10 years and the first 10 years, we see the internal variability of NAO is not independent of global warming. Here comes the result for the first 10 years. So the spatial pattern of some NAO, the sub-center of action shifted towards northwestern Europe, which is also shown in the observations. And the index of NAO follows the normal distribution. And here comes the result for the last 10 years. So we can see the spatial pattern slightly shifts eastward, but the more interesting change occurs in the index. The distribution of the index of NAO in a warmer climate, represented here as a red bar, is flatter compared to the pre-industrial climate. So that if we look at the two tails of the distribution, there are more extreme cases in a warmer climate. Here we define those cases below -1.5 as the negative extremes, and those above 1.5 as positive extremes. So we can count how many extreme cases occur. Since we have done the analysis every 10 years, we can plot the occurrence of the extreme cases as a function of time for both positive and negative extremes. Here comes the result for the MPI Grand Ensemble historical run and RCP 8.5 runs. Although we have removed the externally forced signal or the direct response, we still see the significant increase of the extreme cases, of the occurrence of the extreme cases that is internally generated. Here comes the result for the MPI Grand Ensemble 1% CO2 run, which is driven by a stronger warming scenario. So we can see the increase is even stronger. We also check all the other available large ensemble simulations. The Canadian model with 50 ensemble members shows increase for the negative phase, not the positive phase. The NCAR model shows increase for both positive and negative phase. And the Australian model shows the increase for both positive and negative phase. And finally, the JFDL model. Although it seems that JFDL model doesn't show a clear increase, but here actually the y-axis is the absolute value, absolute occurrence of the extreme cases in all the ensemble members. So if we divide the occurrence by the ensemble size, actually, and then we calculate the slope of this time series, shown here as the rate of increase per decade. So we can see for negative phase, the increase of the occurrence is pretty robust or pretty consistent across different models. The colors are for different models. While for the positive, there are large uncertainties. To check if the ensemble size is a factor to influence the finding here, we resample the 100 ensemble member MPI Grand Ensemble into 20, 30, 40, 50 as the others. And we found actually, due to some techniques we used, the ensemble size now doesn't influence the size of the trend anymore, but it does influence the uncertainty. And also, the positive phase is more influenced by the ensemble size than the negative phase. So the different characteristics of the positive phase and the negative phase may partly due to the different dynamical processes that those two phases are presenting. So the next question is, all those results are coming from the large ensemble simulations. we would be concerned, or one question would be, could we already see some hints from the observations? It's always harder to extract the internal variability from the observations. Here we use the 20th century real analysis data with all those ensemble members. So with a spatial pattern similar to the large ensemble simulations, we found actually the index of NAO in a recent 40-year period, shown here is the orange bar, is indeed flatter than the first 40 years. So the same if we count the extreme cases, in a recent 40 years, the occurrence is indeed higher than the first 10 years for both positive and negative extremes. Yeah, as I said, care should be taken when interpreting the internal variability from the real analysis data. Indeed, if we use the ensemble mean of the 20th century real analysis data, which is the Euro way of using the data, so the increase becomes insignificant. We can also plot the rate of the increase on the same plot as before. So we can see for the negative phase, roughly 3% per decade. That's very close to the model simulations, while for positive phase, the difference is much larger. So we can summarize what we have achieved for now. So the SMILES show increase in the occurrence of internally generated summer North Atlantic oscillation extremes in a warming climate. And such increase is emerging from the historical records. And the negative phase shows more robust increase than the positive phase. So that's for the occurrence of the extreme cases. What about the impact of those extreme cases on the surface temperature? We could check that with the composite analysis. Here shows the surface temperature pattern during the positive summer NAO. So we can see a warming effect over northwestern Europe and a cooling effect over Mediterranean. And such a pattern is consistent across different models. And we could also see that from the real analysis data. And here comes the result for the last 10 years. So we can see this warming effect over northwestern Europe is amplified and extended, and it's also consistent across different models. And we can also see such amplification from the real analysis data. And if we calculate the difference between last 10 years and the first 10 years, so we can see such increase actually is significant over northwestern Europe. So finally, it's our conclusion here. We have shown that the summer North Atlantic oscillation extremes generated by internal variability are changing in a simulated greenhouse warming. The occurrence of such extreme cases increase, and also the impact over the northwestern Europe is amplified. That's all. Thank you.
Thank you, Juan, for the perfect timing. Any question? Yes.
Yeah, thank you very much for this very interesting talk, and I'm really impressed by the results. I wonder to what extent the extreme summer NAO values are an expression of ensemble spread, and to what extent we might have decadal or multi-decadal predictability in the large ensemble that is lost as time goes on, and therefore the extreme values get larger. You see that the signal from the initial conditions is lost, and therefore the spread gets larger.
Yeah, so if we look at the time series of the NAO in the large ensemble simulation, actually, we don't really see the decadal variability, I mean, with all the ensemble members. If you look at one single ensemble member, of course, you can see such very obvious decadal variability. But so what we did here is we had to do the analysis every non-overlapping 10 years. So in these 10 years, the state of NAO could be at any value, basically, if your ensemble size is big enough. So I don't think the result is influenced by decadal variability. And also, actually, I have shown the time series of the occurrence of the extreme cases. So we can see, yeah, of course, there are some deviation, but the general trend is increasing. That's also another signal. So if we just see the first 10 years and the last 10 years, maybe it could be influenced by decadal variability. Yeah.
Thanks a lot.
Other questions? Yes.
Thanks again for the talk. I was wondering about the dynamical drivers of this summer NAO that becomes more extremes, both in the positive and in the negative direction. And the winter NAO is related to the, among previous researchers, related to the momentum fluxes that result from the eddies propagate from the west. So anticyclonic wave breaking more NAO plus, cyclonic wave breaking more NAO minus. I was wondering if you had, if this the relation holds also for the summer NAO, and if you have checked that, or if you have other ideas of why these extremes are becoming more frequent.
Yeah, actually, I already started to take the notes of what you said. Yeah, it's really hard to really already goes into the dynamical like explanation for now. I think yes, there are a lot of literatures trying to explore the dynamical processes behind those NAO index, and also like for example, I found the Tim Woolings has a lot of papers saying how the Greenland blocking is linked to the negative phase of NAO. And for the summer NAO, there are not so many literatures, but I guess the processes could be similar. I have done some analysis to those blockings, but still, yeah, a lot of struggling because we have removed the ensemble mean. And if we look at the either the jet stream wave breaking or blocking, so it's really hard to see if the index still makes sense if you remove the ensemble mean. But if you don't remove that, and then you compare the mean state with kind of the internal variability, it's also, yeah, it's very complicated for now. I'm open for any suggestions, actually.
Given that you were talking about that, indeed there is this positive trend in the Greenland blocking that has been observed only during summer, and maybe it is related, as you were saying, exactly. Maybe it is related also to the trends in the NAO that you see. But yeah, it's great.
Yeah. Definitely, I will check that. Thanks.
Yes, we have another question.
Hi, thank you for the very interesting talk. Yeah, actually, I'm working too on the summer Greenland blocking trends, and I also tried to use the 20CR analysis. That I was wondering, how did you address the problem of the data scarcity in the 19th century? So it's I noticed that it's difficult to have a realistic natural variability in the 19th century. So I was wondering, how did you calculate the NAO index? The data, did you use the single ensemble members used to create the reanalysis data, or you computed it only on the ensemble mean?
Yeah, thanks for the question. So yeah, for the reanalysis data, so we have removed the externally forced signal or the direct response here by removing the quadratic trend from the quadratic trend of the ensemble mean. So then subtract this trend from each of the ensemble members. So I think what you said, some large spread over 19th century, I haven't really checked that, but I do check the variability along the ensemble dimension, not every year, but for like every 20 years. So we found actually this variability along the ensemble dimension is in the same order as the MPI grand ensemble. Although it also shows very large decadal variability, it is expected because of the very similarity between those ensemble members in real analysis data, which is generated by the statistical methods actually. So, but generally, the magnitude of the variability along ensemble dimension is similar to MPI grand ensemble, and it also shows a slightly decreasing trend, which is also can be seen in MPI grand ensemble. And also, I think the important point here is the change of the variability because of the better observations we have had in recent years is actually very small compared to the variability of the NAO, because we know that for one standard deviation of NAO, the geopotential height change could be 40 to 60 meters. But if you look at the variability along the ensemble dimension change over time, this change could be as large as 5 meters or 10 meters. So compared to the NAO variability, such change is actually small. So that's why I think, although as the time goes by, the input for the 20th century real analysis data is becoming better, but still it's fine to use that to explore the evolution of the NAO. Yeah.
Thank you.
Thank you. Other questions? No. Okay, thank you, Kwan. And I want to say thank you to all the speakers of this afternoon. I think this should be the time slot for the poster share session, but we can spend some time for a wrap up of the day and some discussion. What do you think?
Yeah. So I mean, I wrote down some notes, also trying to match with what we discussed yesterday. I know all of us are quite tired, but let's say we try to wrap up with some 20 minutes, and then we go to the poster session at 6:30, if it's fine by you. Okay. Thank you for the support. So what I wrote is that, well, this also comes out of some discussion I had with some of you during the lunch break and the poster, and the coffee break. And I identified basically three communities in the audience, I might say. One community is the one of the dynamicists that are working on waves and Rossby waves, but not only, and also working on different domains. We had this talk by Medielka yesterday that was somehow influenced by the background on the tropics with Kelvin and barotropic swing functions. And then we have the community of climate modelers and climate analysts that are trying to understand how features of large-scale circulation are affected by the climate change signal. And then there are the statistics people, basically, and theoreticians, so to say, from the dynamical state theories, dynamical systems theory, sorry. They are trying to basically find commonalities between dynamical systems of different complexity and how we can interpret them in order to infer useful arguments for predictability and diagnosis of extreme events. I think that the kind of exercise that we could try to do now in order to harmonize the different communities could be identifying some common topics that are, so to say, interdisciplinary, and maybe find some case studies where we could try to work on from different points of view, finding some interpretation that basically brings everything together. So I wrote down some just keywords from our talks from today mainly, but also going back to yesterday, which is the nonlinear interactions, predictability, pattern recognition. We saw many different ways of recognizing patterns in the dynamics and in general circulation. Idealized experiment, which is somehow what Emanuele was showing with his very simple, if I may say, version of icon, and the clustering of heatwave types, typicality and understanding of the dynamics, which I recognize as basically the same thing, but from different points of view. So with this introduction, I would try to leave the floor to you in order to see. Yeah, Simona, please.
I'll come in the front. So this is one thought that I had after we invited the speakers. And so maybe we should have included another category in this, people really working on simple theoretical constraints on heat waves. And so that's where I want, maybe, again, it's really a comment and more the idea to see where people working on heat waves stand on this, the validity of having some constraints or scaling of how, for instance, temperature and temperature extremes respond and behave. So papers that come to mind that have appeared recently are by Zhang and Booth, who provided an upper bound on surface temperature of heat waves in mid-latitudes, in the sense that the temperature at the surface cannot increase. It will stop increasing once the atmosphere becomes convectively unstable, and then precipitation will develop. And basically, they have an upper bound that links the surface temperature to the mid-tropospheric temperature. And then there is the drier, get hotter scaling that might burn develop for tropical land, using constraints arising from the fact that in the tropics you cannot have strong temperature gradients. You actually are bound to have weak temperature gradients because rotation is small, and that really emphasizes the importance of the near surface specific humidity. And so the drier get hotter is simply this idea that ocean and land are bound to have more or less the same noise static energy, which is temperature and specific humidity. But of course, specific humidity is much smaller over land. And so that's why the drier need to get hotter, so to maintain that. And so again, these are just thoughts that I have here, and I was thinking if maybe an exercise that we could do, and that's a question for you, is are these useful constraints? Do they tell us something about heat waves? So I thought I would add up in your categorization, maybe simple scaling, simple theories.
Just a general thought on what you said, maybe not specifically on this, but generally. I believe that it is important to have these different approaches, different perspectives, and I think it is important to try to connect them. So statistical approaches, it's important to connect statistical approaches with physical approaches. And for example, also in the case you mentioned with these upper bounds, you can get with physical, based on physical reasoning, and then you get some upper bounds based on extreme value theory. And then these two should match, and they often do not. So I think both perspectives are important. They both have advantages and disadvantages. I think we should often maybe practice switching the perspective and finding these commonalities.
Any more inputs for the discussion?
It's a long day.
Yeah, very long day.
And it's not over yet.
Yeah, so I mean, if I think of common ground of understanding for these compound extreme events, I think of some examples that have been given today. For instance, most prominently, there were lots of studies about the 2021 Northwestern Pacific heat wave that were mentioned several times, but also in some respects the 2010 Russian heat wave was also a matter of study. And also we saw that there are some regional aspects that matter for some case studies and more global aspects that matter for other case studies. So it is important also to identify to what extent a heat wave is regionally driven and to what extent it is globally driven by using different metrics and different interpretative tools in general. So I mean, I'm now thinking of the SST anomaly over Eastern Northern Atlantic, which is going for, I mean, several months now, and there is, I mean, there are only few clues about why this is happening and what might be the role of ENSO and super ENSO superimposing on that. I think we could also think whether case studies might be in order to increase our predictable power or in order to better understand what has already happened. And I think these are also different lines of thought. Yeah, I'm talking too much. So in the meantime, I'm trying to make the remote poster session working.
We can try.
Mm-hmm.
Okay. Well, I guess this kind of links in this morning, which is it would be nice to generalize what we see in here in the scalings, or but it seems that there is like the global or semi-global effect of this process, but then also in the latitude there's a big effect of moving circulation, changing circulation, and that's just I mean that could be a scaling for that as well, but in general it's a lot more complicated, and but there could be other ways of simplifying our understanding of that, and it seems that like having a simple metric of like how do you relate the large scale circulation to the impacts. It would touch all the opportunities that you just mentioned.
You said impacts, right?
Sorry?
Impacts. You mentioned impacts.
It would be touching the three groups of people that you mentioned.
Mm-hmm.
So if there was for example, if there was a way to like reduce the dimensionality of the variability of the jet, like some sort of like I guess I don't want to say EF, but some sort of common variability to describe what's going on. And you could then look at it from the reading perspectives, you could look at it from the learning perspective, you could look at it from the statistical one, and from the process-based. And that way there would be a bit of an overlap between the methods. And maybe that would lead to some simplified mechanistic picture that we need to scale.
Mhm. Is anyone from the audience remotely willing to talk?
Hi, Valerio. Valerio?
Hey, Daniela, hi.
Hi, very nice meeting. Congratulations.
You're very, very low. Can you tell me?
Can you hear better?
Yeah, much better.
Much better. It was a mic which was hidden. It was a very nice meeting, so I could not follow the full one. But I was just curious when you mentioned the actual warming conditions over the Atlantic and you mentioned ENSO. What did you have in mind?
No, I mean, the thing is that as a matter of fact, we have an ENSO season, ENSO plus season.
El Nino, you mean? Yes.
Yes, yes, yes. El Nino.
But usually El Nino brings the teleconnection to Europe a bit now in, later in the year and early in the year. So if so, it will bring us a bit of cold. And El Nino is developing. I was unsure because, El Nino will not impact, El Nino could not have impacted the warm condition over the Atlantic, just to clarify a bit on that one. From what we know, I was thinking if you mentioned if you had something with La Nina in mind in the previous 3 years.
No, I was just thinking that we have this
El Nino going on. This is what you mean.
months of positive SST anomalies in the
yes,
Atlantic.
but this has nothing to do with El Nino in the Pacific.
That's
true. Usually
that
the impacts comes later, if any, whatever teleconnections from La Nina in the previous 3 years. Just a comment on.
I actually did not.
Yeah, because I'm working on a topic. What I wanted to say, so for example, a couple of months ago in the summer, the Americans have a lot of heat wave. I mean, maybe you have some Americans in the audience or people working in the US, this heat dome, how it's called, toward the southern part of the US. And actually that one is preconditioned by La Nina condition in the winter before. So it's exactly teleconnections. I mean, El Nino was growing in that moment, but did not have a strong impact. But I think we still need to investigate. But La Nina conditions in the winter before could precondition the huge heat wave, speaking about multiple drivers. I find it very interesting. So, and you are right about Atlantic. We have some potential drivers, but we don't know too much. Anyway, very nice meeting. Please continue. I don't want to stop you. Go to the poster and have a nice dinner and discussion. I mean,
thank you for the input, Daniela. Yeah.
Yeah, sure. But scaling only works really in warm climates. I think what's kind of exciting about right now is that we're seeing trends in the heat waves and in the circulation. Most of that's happening in summer, and we don't really know how they're connected, if they're connected, and what's driving them. The heat wave literature, which is very far advanced, I think beyond the summer circulation literature, suggests that half of the heat wave signal over Europe is driven by aerosols. And in the circulation literature, it's basically not discussed. When you have those changes over Eastern North America and Europe, that can drive heat waves. That's a forcing that projects onto a wave number. What is the role of that in our circulation? I think that's exciting. Eric Fisher has papers saying that the circulation damps heat waves. Dr. Fuller, I'm talking about this. Damps the circulation damps heat waves in some regions and amplifies it in others. How does he do that? He does it with a statistical linear regression. He doesn't do it with dynamical ideas, which is not to say that they're not valuable, but I think as a community, that's where we need to play a role. We need to help unravel why that is and how we're getting the right amplitude of these signals, why. So I think it's really exciting to come together in this three-pronged approach to address what's happening right now. Scalings are useful, but it's really important to also think about what's happening right now. And not just individual events, but the kind of cumulative trends are quite clear.
It's a great point.
But then, I mean, how would you imagine working together, bringing, I mean, the expertise, if the topic would be looking at trends and trying to understand them?
Yeah, so any metric, about the waveguides. So what is it about? Are the waveguides changing in a way that can help explain something? And then, of course, why are the waveguides changing? Is it that's an important thing. So I think that's maybe an important connection. Using the same ideas and the same tools, but kind of focusing in on the signals that we're seeing over long time scales. That connects to this huge body of heat wave literature that has been, I think, begging for dynamical people to think about why heat waves are underestimated in models. They keep saying it's the circulation, but they can't say more than that. They don't know. We could be the ones to figure it out if we want to.
So let's say that the matter that we should have to treat would be model simulations, maybe idealized experiments where we really can tune the forcing and do not have any uncertainty about that, and we can focus on the response or something like that. A meet, maybe. Look at Simona. Okay. Yeah, well, I think that. Yeah, Jacopo, yes.
Just to add to what was said, also to what you were saying before, the story maybe we can contrast global, say something like global heat waves or regional heat waves, was it something in this direction? But now the work of Cassandra, for instance, showed that every time we have an heat wave day, very likely there are at least two, three other heat waves around the globe. And we don't even know then. Don't even agree maybe on saying, okay, then this is wave, this is more regional, while this one is global. So it means that it's part of something bigger. And even reflecting on that and find out a common ground to say, okay, then we are in front of a regional phenomenon or a global phenomenon, will be already a great progress. Just to add that.
I'm writing notes. It's not that I'm ignoring you. Any more inputs? From the audience online? Okay, I mean, I see that there are only 9 Highlanders surviving, and one of them is me, actually. So yeah, I think that we could say that we move to the posters session, and we can continue discussions in front of posters, and then we also have a wrap up and concluding discussion tomorrow after the talks, where I hope that we will manage to find some interesting take-home messages. Thank you very much for attending again, and yeah, enjoy the process session. And for those of you who have registered, well, actually, there is some very last thing that I have to show you. I just want to confirm the register keyboard for the social dinner because I have a list, and I share the screen 1 second. I don't control the. Why am I controlling that? Because I'm not seeing that. So this is the list I have. Can you confirm that? Yeah. Right. I don't know. I don't know how to zoom in. Sorry. Okay. Then, yeah, I thank also the audience that attended remotely. We are not registering anymore, right? No. Okay. And we'll see you tomorrow then. Thank you.
Thank you.
Bye.
Thank you. Bye.
Pardon?